So maybe we can start now. So welcome back everyone after the lunch. So we'll have a session on polymer and nanocomposites. We'll have 4 speakers as previous sessions, and the time slot is the same, 25 plus 5 minutes, 5 minutes for question answer. So the first speaker of the session is Professor Mithun Chaudhary from IIT Bombay, Metallurgy Department. He did his MSc from University of Calcutta with a specialization in physical chemistry. And then his PhD is from University of Freiburg, Germany. After that, he did 3 postdocs during the year 2012 to 2018 at several places. The last one is at Princeton University. And then he is an assistant professor at IIT Bombay since 2018. So with that introduction, I'll welcome Mithun and request him to start his presentation.
Okay, at first, am I audible? And
yes,
my screen? Okay,
yeah.
Perfect. Thanks, Sunita, for the introduction. And it was a pleasure actually for me in e-SMYIM, although it's not the it's now in E mode, but I think I had a very good memory with e-SMYIM. I would actually like to tell that a brief line, especially for younger ones, because this is the first time when I started to collaborate independently, although I was a postdoc that time, because I was meeting in one of the e-SMYIM in one of my collaborator, who I am still in touch, Dilip Sadapati in IIT Madras. So it was a nice experience and nice atmosphere. And yeah, we're trying to mimic it as much as possible in this mode. Let's see how it is. Anyway, coming back to whatever I'm going to talk today. So it's basically some work which we are doing, let's say, last few months, and especially when we have opened up about a year for the students. And there I was trying to look into a very old and basic problems, or eventually I would say it was one of the processing methods where people used to put plasticizer, even nowadays they also do, and try to process polymers accordingly, because plasticizers are known to have some general impacts which allow particular thermoplastic, especially thermoplastic kind of polymers to process. Whereas the situation is fairly complicated when you are dealing with a polymer where the dimension is playing some role, especially when your polymer has a nano size dimension. And there we are basically encountering a sort of a conflict. Is that we are really doing a plasticization in a classical way or not? And that I'm going to explain or show our initial results, which are near about to complete, I hope. So before I go into all the things, what happens normally in talks, discussions and everything pops up and you don't get the chance to show those who are at the background and the main driver for these things. So first, the money is coming from a few grants that starts from IIT Bombay to ACRB through different kind of projects. The work is mainly done by Mithun Madhusudanan. He also has a mini talk or in pretty soon, I guess, right after this. So please be there. He will be talking only in this area. So maybe it would be rather a brief overview, sort of crystal clear kind of things. And this thing actually, yeah, I'm not going to talk, just put few images, like it was my sort of SOS research. What could be done when you don't have any supply and everything locked down? So I started to play with simple salts that you can get in your kitchen. And once the experiment has been standardized, you just buy better salt from a nice chemical company and reproduce the result and try to publish. So we are more or less successful on that. Anyway, I'll be not talking about that. So the other student who was involved in this work is also Jyoti Priya. He recently started. So coming back to the thing, in my group, we are actually try to do size dependent properties in polymers, which is basically, yeah, we are not playing with quantum dots and all other exotic nice size dependent nanoparticle related phenomena. Rather than we are polymers, which is in contact with a non-polymeric interface, and the interface which is roughly in the dimension of nano size and at the boundary between the polymer and non-polymer. It could be as a form of a substrate, like when you are making a solid film. or it could be like a nanocomposite when you have nano-sized tiny particles, inorganic particles, and around it some polymers. So for me, looking into those nano-sized polymer and non-polymer interface is basically same whether it is a membrane or supported film or a sandwich or a composite. Of course, there are some differences, and I will not go into the details, but this is the general idea. And I know that at least in this meeting, I mean, my knowledge, there are more people who are also actually working and or have been worked in this directly in this area. So it's a pretty exciting area. There might be more, but I can certainly tell that Shiva, Surender, and Sunita was also is or still now they are also dealing with this kind of problem. So the problem which I mainly look is try to find the what is the phenomena is happening in this kind of nanoscale features in terms of glass transition, or I would say that process related to glass transition. Means, yeah, if you think in terms of a characterization aspect, you heat something up and you get a sort of a change in slope and some change in behavior in the specific heat, and that is your defining your glass transition. But you should also be sort of thinking that there might be other kind of process related to it for sure. So because it is also related to your viscosity and the flow, which is related to your motion of the material, something like that. So as a whole, beyond the your fundamental picture in this process, there is also something very interesting, because this kind of dimension is also technologically very relevant. And that's why uh, whenever you are chasing these fundamental questions related to glass transition and related properties, you are also somehow helping people to understand the thermal stability of those kind of material, or rather than you are defining the way it should have to be uh, fabricated in such kind of really geometrically different kind of dimensions. Okay, I was talking a bit on glass transition, and I think, I mean, I should have some time to tell a bit on that. So let me put the pointer. Here you go. So it's basically the interesting thing in glass and liquid is that although I don't have the scope to go very detailed, but let's say for our case, you can think that it's a material which has a molecular level ordering, whether it's a glass or liquid is just the same. The only difference is, of course, you can understand the glass is a solid. It has some ability to hold some shear strength. It has eventually high viscosity compared to the liquid. Even your solid cannot flow. So if you compare their viscosity, there will be at least 12 to 13 order of magnitude difference, especially on the system of those fragile molecules, like small molecules of polymer we are dealing with. So in general, if you also coming from your potential energy landscape background, you can say that how it should roughly look like. When you are out of equilibrium, you are in metastable, it's really an unhappy situation, you are not even in the valley. Whereas when you are liquid, you are happy, or if you are can form crystal, you are the happiest. So these are all like a sort of a hand-wavy idea. So the idea is that if you can really cool a glass fast, you will be really, really far out of equilibrium. And that is the place from where you are reaching from out of equilibrium to the extrapolated so-called equilibrium line. All the strange phenomena are happening there. I mean, of course, you are in the solid state, but you are at molecular level, you are doing a lot of things. And that's why defining glass transition is not easy just by thermodynamic picture. It has some uh, time associated with, let's say we call a characteristics time scale, and also characteristics length scale, which is related to the molecular level motion of the polymers, in my case polymer. But why I explained you glass transition? Because I am trying to say a way people used to manipulate glass transition, and that is basically plasticization, which if you just look at the references, I mean, and just look at the years, people used to play with that 60 years before. Yeah, in 50s, 60s. Yeah, nowadays also people do that. So the idea was that if you just follow a so-called definition, it in general refers to a change in the thermal and mechanical properties of a given polymer, which involves lowering of rigidity of that polymer at room temperature, lowering of glass transition temperature, or giving it some sort of ductility, so that it become less brittle, or its toughness do get increased. So toughness is basically your area under the curve when you are doing stress strain plot, but also beyond linear stage. And brittleness, you also understand that if you have a very brittle thing, you can do linear elastic fracture. So people in those earlier days, they tried to look into this problem that mainly related to glass transition. Means if you mix something in a polymer, or yeah, let's say in our case polymer, you will be making it rather more non-polymeric, because you have a long chain, and in between the chains they are like a coil, and you are putting some small molecule into it, and basically you are making it less polymeric because they are becoming more flexible. You have put some stuff inside it, they are all the entanglement or knot kind of things, they become little less or become more fluffy. So it's basically you essentially making your polymer towards more non-polymeric things. And people used to calculate this efficiency of plasticization in terms of glass transition temperature. Means they used to do a sort of a rule of mixing. Means you have a polymer A, you have a small molecule B, you mix them. Now what would be the average? Now there is, whenever you do this kind of average, you always have a upper limit and lower limit. Upper limit is basically your inverse summation average, and lower limit is basically your linear summation average. So that is basically your inverse summation is like your Florey-Fox law, or if you go the linear one, that's your Yankel-Hughes law. And all the case, yeah, you will always get some extra factor, which is just basically compensate the extra effect. And I think this is one of the culprit. People didn't know at that time what the extra effect is. There are many thought kind of models for plasticizations. Somebody said that it is making it little gel-like, it is rather connecting the knots between the polymer, certainly not cross-linking. But as a whole, no clear molecular level picture like as you have in for normal polymers in solvent and their interaction in terms of radius of gyration, in terms of light scattering. That kind of detailed literature doesn't exist till days in plasticization. Yeah, some kind of thing exists when you have especially a plasticizer interacting with a polymer. But when you mix them in a polymer with solvent, the situation becomes more and more complicated. So now let's come back to the our kind of system. Why it is complicated? Because in thin film, people found that the glass transition temperature is even different than bulk. Below 100 nanometer roughly, they found that TG certainly decreases. And of course, there it also depends upon kind of interaction of the substrate and polymer. Is it like doing any kind of hydrogen bonding or not? But this general scenario is mainly for polystyrene on top of silicon wafer, where you don't expect any extra chemical interaction. It's just a physical interaction. And I would say it's rather neutral kind of interaction, not a repulsion, not an attraction. So the idea, people also like, there are many kind of thoughts, and the original paper in this area came out on 1992, but I think there are after that about 2,500 citations already. Many kind of analogy. One of the analogy says that you have a sort of liquid kind of layer at the surface, and you are rather losing your liquidness when you are going down from surface to your substrate, because at substrate your polymer is getting strongly attached with your non-polymeric substrate, which is in general, let's say, silica wafer and silicon wafer. And so you are sort of killing your polymer, making it dead, and you are losing its mobility. In fact, there are other literature which says that if you are killing your polymer gradually by doing more and more adsorption, you are not even going to see that TG decrease effect will film thickness. You will just see that TG is comparable to bulk even after changing the film thickness. Why I am saying so, you will see that because this effect has been already seen when plasticizer has been added. I will come into the picture, so you have to wait for that. So yeah, I think it's already came. Oh, how lucky I was. So the thing is that if you look at the almost left panel of this thing, here in one of the paper in 2004 PRL, Ellison and Torkelson showed this effect when you have like the film thickness reduction and TG reduction. That effect, of course, is clear on neat polystyrene, but if you try to add your plasticizer, you are losing the effect. So they added 2% DOP. DOP is a very standard plasticizer whose full name is dioctyl phthalate. And it's like, of course, a small organic molecule, and it has been used for many kind of polymers, mainly PVC and polystyrene. So whatever is clear here, you can see that when this guy added 4% DOP, the difference between TG and TG bulk got vanished. Okay, what could be the explanation? I told you that irreversible adsorption kind of thing, or polymer, when becomes more dead-like, they are no more, they get stuck, then they lose the TG reduction. But of course, when you are adding some molecule, you don't expect that will probably help your polymer to get absorbed. Rather, it is making the system more diluted. Maybe it is becoming sort of a fluffy thing. But why there is no more decrease in TG, that is not clear. Eventually, why TG decreases with film thickness, that is, there are many theories, many experiments, many successful experiments. The idea is eventually not clear yet. Now, that was the aspect of TG, means thermal stability. But as I told you that there are other things like flow. Flow is viscosity. Viscosity should be related to your mechanical property. The other thing we usually invite with mechanical property is the modulus. When you are at the solid state, I mean below the TG, you can easily define those as elastic modulus, especially when you are well above TG, you can correlate that with shear modulus. So this set of experiment at the center, you are seeing that with change in film thickness, there is a decrease in film's elastic modulus. These experiments are done by Torres, Stafford, and Voigt. But when your DOP amount is increasing up to 5%, which is rather close to the 4%, you don't see a change in your elastic modulus. Although the axis is, the film thickness axis is not logarithm like the TG one, but qualitatively the trend is somehow saying that adding this plasticizer is actually taking out your TG reduction with film thickness scenario. Whereas there are some viscosity measurement done by Shui in the rightmost panel. There you can see that with respect to thickness reduction, and I know that they used 4% DOP, the decrease of viscosity is still there. And I would say that the only thing is that their viscosity is calculated with a tri-layer model, which is a very model dependent viscosity. But I think they are pretty successful to establish this protocol. So you can already see there is a discrepancy. Your modulus is saying something, your TG is saying something, and viscosity is saying something when you are comparing with the film thickness. Now, what I am going to do here, I mean, of course, I am not going to measure TG. I mean, I have planned, but you understand that measuring TG in the thin film is not like your real life bulk TG measurement with powder. It needs a little bit of different kind of setup for thickness measurement, or nowadays some nanoscale DSC is also possible. So I thought, okay, I will jump into the domain where I can see how the flow is happening inside those films, and rather stay close to viscosity and your modulus. Because anyway, if I somehow solve this part out, the TG part is more or less established, because that was just observation with sort of argument. So here two things will come up. Again, I am referring this Torres paper. They found that if you add more and more DOP, means you are adding more and more plasticizer, their modulus is basically decreasing, which is actually, you probably will accept it wholeheartedly, because you are making the polymer more and more weak or non-polymer, and that's why your modulus is decreasing. Now, another thing comes up, especially when you are dealing with this thin film. There is a term people define as residual stress. Now, residual stress in general is a very vague term. It could be eventually your thermal stress, or thermal mismatch stress coupled up with few other factors, which like intrinsically you generate if you have a very thick material, let's say drying induced stress, all could be termed in terms of residual stress. But these people, or me, or in probably in this session pretty soon, probably next talk, you will be hearing from Shiva Surinder, we have defined residual stress in a little different way. We actually consider this is a result of non-equilibrium chain conformation in polymers. Means basically, you have polymer in solution, you are spin coating, and you are doing glass transition eventually during spin coating. In very short span of time, you are getting rid out of all the solvents. Your polymers now cannot be that heavy as it was in the solution. So they are falling out of equilibrium. And those such nice coils, which you normally expect as your radius of gyration kind of cartoon, they are sort of now tilted, poorly entangled, giving you some residual stress. So if I try to look into them like in terms of schematic, they are like that. So when you are in thin film, you are like this kind of poorly entangled situation, whereas in bulk, you have the left panel. Eventually, hand wavy calculation, if you just try to calculate overlap fraction, they can give you in the similar sort of picture. Geometrically frustrated, giving you a poor entanglement, and probably that is giving you a sort of a strain inside the polymer chain, and that is related to people termed it in different way. Some eventually don't even call it strain, they call stress, and other one is recoiling strain. So anyway, these are the general picture, and there are actually serious amount of work has been done by yeah, this is my old slide, so I should actually also refer. There are tons of advanced paper by Shiva recently done. So its general idea, it has been shown that when you are have a film, thin film, and you are actually heating it up on top of a compliant substrate, means you have a very nice liquid layer on top of silicon wafer, and you are heating the film above the glass transition temperature, and you are actually creating a hole. And of course, it's a liquid, so it will be circular, hole or drop. And by looking into the growth rate of the hole, you can actually comment in about the strain inside the film. So now what is that? I mean, how can it is? Like when you are in a general case, you are like, let's say you are putting water on top of a surface. The way the water will dry from the surface, that is related to the capillary force, because of course, capillary surface tension that is responsible to drag a liquid on top of a substrate. But here, I mean, the community has been successfully shown that it has an additional driver, which is coming from the same thing which I was talking, the residual stress or residual strain, sigma res over E, then it's a strain. And that's an additional driver. Means if you have more and more strain inside the film, you are going to get higher speed of dewating, because your capillary portion is nearly constant as long as you have the same film thickness. Now you are thinking, is it like a nice flow of the liquid? Is it really liquid? It's actually not, because you can see if you look at the size and shape of this portion, which is basically this darker portion here, we call it like a rim, because it's basically you make a hole and then you have the substrate there, it is creating friction and some material is getting accumulated around and making a rim. And if you look into the rim, the shape is pretty asymmetric. And if it is a perfect liquid, you couldn't see that asymmetry, because the Laplace pressure will allow you to roll it up very nicely to get a sort of a symmetric shape. So that says that this material still has some elasticity. So we would say that this is rather a viscoelastic phenomena, where it actually also supports the idea of having the strain, which you can probably also correlate from the geometry, that sigma over E, and depends upon how much material you had and how much material you have now, and that you can correlate with the shape and size of this rim. Okay, so let's say agree with the fact that if you have higher growth speed and let's say higher amount of height of the rim, larger.
About a minute, if you can conclude.
Okay, basically I have exaggerated too much, so let's say I have to conclude pretty soon. So so that says that that was the idea. When we have added plasticizer, we also got this thing, and we have seen that our rim shape is still asymmetric. Now the problem comes, I mean, as I said, that we are getting a slope at the early stage of dewating, which is about -1, varying from -1 to -2. Okay, so if you think about the residual stress dominated dewating, that should be about -1. Eventually in discussion in future, we can tell that -1 is rather showing you something related to residual stress dominated motion, but we are getting more than that. And with the increasing amount of plasticizer, we are getting this slope higher and higher. And the initial portion where the V stays nearly constant, we call it maximum, they are also staying more or less constant. Sorry, they are also getting increased with more amount of plasticizer. So that's a bit of confusion we have. I mean, as I have to conclude now, and I am not going into the theoretical details. So that is our main data, I would say. With high molecular weight films, we are seeing that there is a portion where this initial portion of slopes are changing into a rather comparable slope of -half, showing viscoelastic. Before that, it was all showing really different kind of relaxation, which may not be residual stress, maybe some extra other kind of thing, which is still in the elastic regime. So with that, I would say that I would rather jump into the conclusion case, saying that the conclusion is rather asking you that maybe at the early stage of your thermal instability, you had some effect which is not as clear as a plasticizer effect, because in that case, you always say that, okay, your velocity of the duetting would be increased, but maybe you will get a really less rigid framework, but our slopes are not probably saying that. Okay, with that, I would stop and take questions.
Thank you, Mithun.
Yeah.
If there are questions, we can take them now.
Yeah, so can I ask?
Sure.
Yes, yes.
Okay. So yeah, Mithun, I think let's if you could again share your slide and then go
Sure,
to your,
I have done that.
Excellent, thanks.
Yeah.
So looking at these plots, one is pretty clear that like you really have a rapid retraction when the hole is starting.
Mm-hmm.
And then later on, there seems to be really two different processes which are coming. So when you think about the process and you're putting in DOP with PS, you know that if there is any possibility of phase separation because of the shear flows which are induced by deviating, I presume these are holes, right? Yeah, holes.
Yeah. Yeah.
Okay, so then is it possible that like you're creating lower shear stresses because of the phase separation at the three-phase contact line?
Yes, I mean, this is one of the things we have thought, but the situation here is like, it's not only pure PS and DOP phase separation, you also have toluene, and there that is the largest amount. I mean, maybe in the film you completely got rid of toluene, that is the general consideration. So now when the hole is growing on, I mean, there is no visible phase separation, but if one can calculate the chi parameter, there would be, for sure, there would be some interaction. But what the question you are asking, that is that phase separation?
No, if there is a phase separation which is
then
happening, so then you would expect the transition, point number one.
Mm-hmm.
And if there is phase separation, then you have to deal the system in a different way.
That's true. But in that case, how do you, I mean, you can probably do scattering to get a phase separation which is not visible by your microscope.
AFM should do, no?
AFM should do, but in AFM we haven't got. We have something.
Okay. So AFM, a simple phase contrast real time would do.
Yeah, that's a good suggestion, but I think we have done. Preliminarily, we have said it's probably not there, but probably for the higher ones, we have to check.
Maybe.
And another thing, yeah, go ahead.
No, just looking at your radius and the velocity, I don't think they are quite matching. So there has to be, I think, some kind of enormous averaging is done in the numerical velocity. So if you look at 20% DOP and PS, I'm sure the velocities are quite different.
Yeah, because
especially
they are falling.
The initial time.
Yeah, at the initial time, they're pretty falling. So it's probably some averaging or whatever.
Yeah.
And yeah, I have to catch my student on that. Yeah. On the other hand, yeah, as you can see, there is a general tendency of this, whatever VM or slope with respect to amount of plasticizer. But this has been already also shown by rim width. You know what the situation with the rim width is. So we have seen also a transition around 100 seconds only when you have the plasticizer. But when you don't have, it was like farther 100 meg higher.
And which goes along the direction that you would expect.
Yeah.
Right.
Yeah.
Yeah, so I think the initial acceleration in your deviating is all that one has to think about.
Yes, I also think so. These 1.5 or 2 minus 2 slope, that actually giving me some trouble to even assimilate the idea, and I couldn't show, but I can also tell you we have also for sure checked with the ultimately low molecular weight films where you don't expect that much of roller residual stress like 56 kD. And there also you can see that there is an increase in speed when you add more and more plasticizer. The reason is, of course, in terms of pure viscosity, that is also allowed. But the VT slope here is about zero point 0.7. I think it's probably interfacial friction because it's not the classical slippage viscosity thing which you expect.
Yeah, I think I don't want to take more time, but we can anyway catch up.
Sure,
But
we
what
have
you
to
can
catch
actually
up. We have to
predict
catch
is
up.
that, like, you, since you know the exact amount of fractions that you're putting in, you can actually theoretically calculate what is the deviations in viscosity that you're expecting if you have a homogeneous dispersion.
That
So
actually I
then
have
one
asked
can
my
try to
student to
see.
do.
Yeah.
Exactly
Okay.
the same thing I have asked them to do. But anyway, we will be in discussion. I mean, that was the plan actually. Sure.
Okay, thank you, Mithun, for this nice talk. Now I'll request you to take over the session for chairing the remaining 3 talks.
Perfect. I can definitely do that. I guess my sharing has been off, and now I can straightforward go to introduce Nirmallo.
Mhm.
Okay. So let's welcome Nirmallo here. Nirmallo has joined IIT Jodhpur, and Nirmallo did his PhD from IIT Bombay and Master of Chemical Engineering from Jadavpur University. Before that, he also had a bachelor degree in chemical engineering from Jadavpur University. He's interested in nanomaterials, polymer nanocomposite, and shelf assembly. And today he is going to talk about elastic response of polymer nanoparticle composite sponges, where it looks he's going to develop some microscopic model to investigate the large deformations. So Nirmallo, the floor is yours. Please take it away.
Thank you, Mithun. That's a nice introduction. And I also like to thank the committee for inviting me for this talk. So as described, I'm going to talk about some inorganic sponges rather, and the elastic response of the sponges for that matter. So before going into the presentation, let me just introduce to the contributors. So the major work of this problem is essentially done by Anish Sukumar, who's in the left side of the panel. And he is a BTech student, third year BTech student. And most of the simulation is done by him. And rest of the things are worked with my postdoctoral advisor, Dr. Guruswamy, and Apratim Chatterjee from ISF Pune. So let's dive into the presentation. So I'll be talking about porous polymer nanocomposites, which is basically a subsection of aerogels. Right? And what aerogels are essentially made through this sol gel technique. So you start with a dispersed system where you have a dispersed phase and a continuous phase as a solvent, and you do a gelation. And by gelation, it forms a sort of network like by continuous phase, and then you do some kind of evaporation or supercritical drying for that matter, which leaves the porous network intact, and therefore you now have a network which is filled with air. So hence the name aerogel. And as you understand, since you have a mixture of, you have a porous structure which has a bunch of air in it, that will immediately reduce your thermal conductivity. It gives you a large surface area, as well as it has a high adsorption capacity. Therefore, there are plenty of applications of such material, and these materials are often used in space, so space vehicles, space suits, and then since these are like flexible materials, they are spongy in nature. So some like flexible semiconductors, not semiconductors, flexible supercapacitors are also can be made from this. This has high adsorption capacity, so it can be used as absorbing material as well. So you can see the application of these kind of materials are huge. And today we'll be talking about a specific system for these inorganic sponges. So these are made by in Guru's lab in 2014. So basically what you see is a cross-section of such sponges, which is again porous and continuous. So they are connected, interconnected pores in there. And this material is essentially made out of silica particles. So if you zoom in, you'll see the material is basically made out of these silica particles, which is held by a sort of small amount of organic material there, organic cross-linkers there. So the way you can imagine this entire material is comprised of about 90% air and 10% material. And this 10% material, out of this 10% material, you have about 95% silica particle and 5% plasticizer. However, so basically the way you make these things is by ice templating. So you disperse these silica particles with some coating agent, which have them well dispersed in the material in water, and have some cross linkers along with it, and you freeze it then, and therefore this ice crystal forms and it grows, pushing these particles into their interstitial position, therefore creating this nice network-like structure, which is what you see over here. And once you have this particle formed, your cross-linker therefore stitch them together to form this network structure, and then you melt the ice, you have this porous structure, right? So it's interesting that you have a structure which is completely made of, almost completely made out of inorganic material, or silica particle in this case, and you have this 5% polymers, and it still behaves like a sponge. So here is a video of that system. So as you can see, if you apply uniaxial compression, it can actually compress almost up to 90%, and once you release the compression, it recovers completely, right? So this is the work which I was referring to, and this is the stress strain curve. So therefore, we wanted to model this system. Now, at the best of my knowledge, there are no models actually existing here, right? Now, the reason is fairly simple. You are actually dealing with a immensely large length scale here, right? So your crosslinker, if you think about your crosslinker, they are in length scale of angstroms. Your particles here, what particles we are talking about is like about 22 nanometers, so they're in nanometer length scale. Your voids are roughly in length scale of microns, and this monolith here is roughly in length scale of millimeter. So you're talking about huge length scale variation, right? And addressing such problems are tricky, and therefore people are not interested. So since it's our system anyway, we wanted to model it. So we started looking into it like this, right? So can you see my screen? Yeah. Oh. So what we did is we started first setting up the box, and in that box we fill the crystal structure of the ice crystals here, and we took a simplistic assumption. We assumed that the ice crystals are spherical and exactly same in size, and we put them into a cubic lattice just for the simplicity of the system, and then we fill the rest of the space with this silica particle in a HCP structure, right? So they are well organized. Before you apply any stress or strain or any equilibrium, you are doing an MD simulation. You are basically setting up these crystals first, and then you add these nanoparticles into the empty space, which is an HCP structure. Now, what I do is we ran NVT ensemble, and we ran about 100,000 state, and the objective here is to randomize their distribution. So we started with an organized distribution, but we want to get into a randomized distribution, and the interaction between this particle is basically like a hard sphere model. So this is called WCA potential, which is like a truncated, only the repulsive part of your Lennard-Jones potential, right? And this last two term is just to make sure that you have a continuous function. So anyway, so once we randomize them, and then we remove these ice particles, which is again same as experiment. So we remove these particles and we stitch these particles together with the polymers. So then we set up a cutoff and stitch them together with a harmonic spring like this, right? So once you have created this network, this particle can then hold on to each other on their own by the virtue of these cross-linkers, and they cannot go into the void anymore, right? And then we run our NVT once again, about 200,000 MD step. Once we equilibrate our system, we get a pressure of the system. And using that pressure, we again run an NPT ensemble to get our equilibrium structure. And what we get is something like this. So we have a box which has about 27 interconnected pores, or the voids, if you mind. And there are like the junctions are the place where you have a lot of particles, and the bridges are the thin. Can you see my? Yeah. Okay. Just. Okay. So the bridges are these thin junctions. So once we have this, we can. We now let me. How do I play this now? Okay. So now we apply our uniaxial compression. So here what you see is multiple different planes, what you're looking at. So the top left is your XY plane, and the right is your ZX plane, and the bottom left is your YZ plane, and this is an isometric view. So now look at, if we apply the strain, what you strain in X direction, what you see is the pores are getting filled. And the interesting thing to notice is the box size is increasing only after the pores are all filled up, which is an interesting phenomena, which even Rajmanikams have found that unless you completely fill out the pores, your Poisson ratio remains almost to 0, which is kind of understandable that unless you fill the pore, the material doesn't stretch in your Y and Z direction. And that is something which we find in our simulation as well, right? So now let us look into the actual stress strain curve. So the right-hand side, you have the Rajmanikam's paper, where you see this stress strain curve as you increase your void fraction. And by increasing the void fraction, what we're doing is decreasing your nominal density, which we intend to use in our work here, because we'll show why it is important and towards the end. But for now, we can understand as you increase your void fraction, your density, the average density, the nominal density, what we call is like number of particles per unit volume, is decreasing, right? So therefore, you can see that qualitatively our data looks exactly the same. So as you increase your void fraction, your stress response kind of drops out, and what you see here is the same. Only thing is there are 3 distinct regimes that we find here, which is not present here. What you see here is roughly 2 regimes. So we will describe these 3 regimes mostly in this work. So what you see here is there's a small linear regime, and then there is a plateau regime. And to show it clearly, I can there's an inset here which shows that the slope clearly changes from initial linear regime to a sort of plateau regime where curves kind of get flattened, and then you start getting up towards the, you see an upturn, and we'll describe this later on. So let's first look at the linear regime. So again, we started plotting this rho versus the rho is the nominal density here, and the the phi V is essentially the void fraction. And I want to inform the audience clearly that this is a correlation which is kind of obvious as you increase your density and your void fraction is decreasing. And this is kind of being used back and forth. Therefore, I want to show it up front. And what you see in the left side y-axis is plotted is the transition strain from the first linear to the plateau regime. And we will come back to this later when we talk about the scaling a little bit. But right now, let's just assume that this is what we see, observe. Rather, we would talk about the modulus with the nominal density. And you can see that so here the nominal density is nominal density at strain equal to 0, right? Or time equal to 0. So this is the initial nominal density, and we're plotting the modulus with it. And it turns out that there is a linear correlation with the modulus. And this is something similar which was found by Rajmanikam's work as well. And the reason is given as, from a mechanical system, if you have a structure like a porous structure like this, if you the walls or the strands at which they are connected, and which is directly parallel to the axis to the strain, if those strands get compressed, you get linear correlation. However, if those buckle and deform the structure completely, then you get a sort of square or higher order relationship, square or cubes and so on and so forth, right? So what it essentially says that our system has a tendency to compress, and at least in the beginning, tendency to compress rather than buckle the strands. And this is also captured through our simulation, right? So we will try to explain this later in a little bit detail. Right now, we have a proof which shows that this is matching exactly what these guys have found earlier, right? So now we come to this plateau regime. So to understand this regime a little bit better, what we did is we plotted the G of R, right? So this is the radial distribution function, and we plotted it for different strain values, right? So what you can see, these peaks are essentially corresponds to the first nearest neighbor distance. So basically the interparticle distance between the first nearest neighbor and the second nearest neighbor and third nearest neighbor and so on, right? And as you understand that if you apply a strain, you compressive strain, essentially, you should expect the particle to come in closer, which is what you see here. So the inset is basically showing the first peak over here and how it is actually moving close together, right? So what we did is we took this first peak itself and estimated their distance, interparticle distance of the first neighbor, and averaged it out for our entire system and plotted it. So this is the mean interparticle distance, which is varying with strain, and we plotted it for all different strain regimes. And interestingly, we see the same behavior. So we see three regimes. So first is an initial slope, although it's not crisp clear, but you can see a sort of a different slope, which is over here in the first 10% of the strain. And then once you go about 50% of the strain, then you get a solid response sort of thing, like it's increasing rapidly. And what we attribute it to is the first part is the compression of your system, and then is the buckling or the deformation of your void. And then once you go to a jam state, when your particles cannot go escape each other, your entire void is gone, then you should see a solid response, right? So let's look at the void deformation first. Now, the way we characterize these voids is by looking at the interfacial particles there, right? So you have these large voids, and these voids are have a skin, and by skin I mean the first adjacent layer to the void, and we tag those particles, and we're just showing a video of it as you compress them. So it's only compressing about 30%, not more than that, because beyond that the things get completely messed up. So what you're seeing here is again three different planes, and this is the isometric view. So as you compress, you can see initially the shape kind of remains spherical, and beyond a certain point, it kind of deforms, and eventually you can see that they are getting almost flattened out, right? So this is what we now characterize. So we characterize this void deformation. So what we do is we take this gyration tensor of this interfacial particle, which is basically saying how the particle move in a flock of particles. So this is your gyration tensor. So what we do is we estimate these three eigenvalues of this matrix G. And once we do that, we take that largest to the smallest eigenvalue ratio. And this is what we plot as a function of strain, right? So this is for the largest nominal density, this is for the smallest nominal density. And what we see here, there's a common trend appearing for both cases. Although the values might be a little bit different, but the qualitative trend in both cases are exactly the same, right? And what that trend is, that says that roughly about 3% and so on, this ratio is kind of remains almost 1. That means they're still decreasing, shrinking in size, but their form is not, this is not completely deformed. From 4 to 12, your eigenvalue ratio is kind of changing to 2, but it's still not completely deformed, right? And beyond this 13%, you see complete maze. So this basically goes everywhere. It goes in different direction, and we are basically plotting here all 27 voids. So this is a ratio for all 27 voids in our box, and they are basically showing. So there is a trend up till about, let's say, 10%, beyond which the void gets completely distorted, right? So basically, what we are saying here from this is that this up to 10%, what you see is a compression of the system. So you still remain as a spherical void, and what's happening is your particle distances are decreasing in size, and they are coming close together, and that's why you get a linear response. That's what they have found in their earlier experimental data, right? And beyond this, your void is getting kind of deformed, completely deformed, and that is where you start seeing a plateau regime, because the interparticle distances are not significantly changing until and unless the two surfaces come close together and completely coalesce. Then that's a different kind of interactions that we are looking at. So that's where you start looking at. So once you go into this jam state, then your strain basically shoots up, and you get a solid kind of response, right? So again, then what we did is we increased the spring constant to see what happens. So as we can intuitively understand that if you increase your spring constant, you make your system stiffer, your solid response will increase, and indeed it increases like it's shown over here. And if you again increase your crosslink density, that means the number of crosslinks that you have per particle has increased now. And that means you have your sphere of influence has increased. So the cutoff radius has increased, and therefore you have more particles to interact with. Therefore, again, you're making your system more stiffer. So if you increase your crosslink density, your again stress response gets like you get a stronger stress response. That's what you see here. So now let's come to the interesting part of the system. So the scaling, right? So now this is an interesting scaling in that for us, because we didn't expect this. This is not something which you can intuitively say. So let me explain the plot first. This is a bit different than what we are showing here earlier. So this is the x-axis is no longer the nominal density. It's a shifted density. So because each of the system has a different density altogether at the beginning, right? Before when you have zero strain, you have a different density. So in order to match them up, you have to basically shift your axis. So that's what we did. So now everything is starting from zero delta rho. That means all of them has been shifted a little bit in your x direction, and the y axis is being scaled by as a multiplying factor. And turns out that multiplying factor is kind of have a inverse square relationship with the nominal density 0, right? At time t equal to 0 or strain equal to 0. So this is and you can see that they beautifully match up, right? So it's not something we have 5 different systems and all of them kind of match up. So not only just for when we change the spring constant, when we change the cross-linking density, still the same kind of relationship holds, which is a very interesting phenomenon, because now what it says that there is a generic phenomena over this whole system. It doesn't matter where you start from. You still have, of course, you scale. You have a scaled response, because now you have many more particles to deal with, many more springs to deal with, but they are just getting scaled up by a constant multiplier, right? So it's like just a linear scaling up. That's very interesting. And we see that they kind of match up all together. However, the physical origin of this kind of slope is not understood as of yet. I would really love your input in this if you have any. So we can discuss it later on. And so then we just summarize the whole thing. So we have basically these 3 regimes, and we explain these 3 regimes. So the first linear regime is coming from the uniform compression of the springs. The second part is coming from this plateau regime, which is coming from this compression of the voids, and the solid regime, which is coming from the jam state when we completely coalesce this void, right? And then we see unexpected scaling of this scaled stress rather, with this delta rho. And we still don't understand. We have observed a scaling relationship. The prefactor of the scaling is which is inversely proportional, square proportional with this rho 0. However, we still don't understand the physical meaning of this. So with this, I'd like to thank you all for listening. I'll take any questions if you have any.
Perfect, Nirmal. Perfect in time. We have the full 4-5 minutes for discussion. Is there any questions? Please go ahead.
I think Danny started.
Yeah, sure.
Nirmal, your nice talk. I was wondering, in your model, are the pores connected?
Yeah, they are connected. Yes. Yeah.
Oh, okay.
So they are connected.
So they form these tortuous paths and so on. So have you characterized this porosity? Like, how is it? Is there any structure to it?
So they are basically, you can assume that two spheres overlap with each other with a small sliver in between them, right? I'm sorry I put it in here, which is not connecting. They are actually connecting. Just to make sure that they are understandable. Otherwise, it's very difficult to understand a 3D phenomena in a 2D phase map.
Right. And if I understood right, there are harmonic, your VH, which is your
Yes, it's a harmonic, yes.
and other forces to make sure they don't overlap. Right?
They cannot overlap because of this hard sphere repulsion, right? So they cannot come. So the particles cannot come overlap onto each other.
So, I mean, when I look at it, correct me if I'm wrong. Let's say I take a block of some arbitrary material and punch holes in it.
Yeah.
It looks like your model would fit that also. What is special about this material system that comes in? I mean, I've missed that part of it.
No, it's really not. I mean, to be honest, there is not much of a difference between a system where you punch some holes into it and then look into it, because that's essentially your spring. This is essentially how you have your sponge, right? That's how you make the sponges. Only thing is here, what we did is we try to mimic the experimental methodology. So we had some sphere, and therefore the particles cannot go into that sphere because there's this hard sphere repulsion. Otherwise, it's exactly the same. Making might be a little bit difficult. If you want to punch some holes into a pre-existing distributed system, bunch of spring gets cut, bunch of things get cut. So making it might be difficult. So this is just a methodology by which you make it. There's no specialty about it.
Shiva, go ahead, Shiva.
No, but I think just extending Danny's perspective. I mean, like if you think of from the perspective of this mechanical metamaterials, right? So these are the systems where essentially means it's an extension of the idea that Danny was proposing, that you just punch holes, but you actually design them appropriately, and then you see like contrastingly different behavior to whatever that conventional systems are showing. I think your model could pave ways towards modeling mechanical metamaterial systems. Right? I think that's just one possibility, but that would be an excellent route.
Beautiful insight. Yeah, thanks.
Nirmal, I have a little query. So the lateral dimension, you do clip it, or I mean, they are not. I mean, you have defined a rigid box. Is that?
Oh no! I forgot to mention. There's a periodic boundary condition in all 6 directions. I am so really sorry. They're connected.
So I have a couple of questions. So if you could go to your slide 9. Yeah, no, the one before.
Yes, yeah.
So here, if I'm looking at your, the free volume change with respect to the change in the density.
Yes.
So you're changing the density almost by like 50%. And your free volume is changing nominally. Okay. So
the thing is, you start with roughly a small amount of material to begin with, right? So this is the density is gram per cc here to relate it to a real system. So this taking into account of the mass of the silica particle, which is quite heavy than air. So they get scaled quite a lot. That is number one. However, the void fractions are essentially about the amount of void that you have. So I'm not sure if I am explaining it correctly. No, so the void is dimensionless. This is with dimension, and you get scaled with the mass of each of the fraction.
Okay, maybe. So I understand what you're indicating. Okay, so if we just go to your the interesting scaling part that you are showing.
Yes. Just give me one second. Yeah.
Yeah, see, I'm just wondering, I mean, maybe I'm just thinking out loud here. So, you have this porous structure, and when you're compressing, you might be having the, if you can define like, new number of contacts which are achieved. Right?
Well, to be honest, there is new number of contacts, but the interaction between them is only accessible when you're talking about this WCA potential, right?
That's
There is
true.
no new spring which is getting connected. So springs are, yeah.
No, there's no new spring which is getting connected, but I think what is happening is possibly that, like, you're you are seeing that there is an increase in the stress. So which is clearly that, like, there is a response of the stress is like a response of your system, right? And
Yes.
now that response is coming just because of the number of the contact, the nearby contact.
Yes,
Nothing
absolutely.
else, right?
Absolutely,
so now if
yes.
we can define, for example, a number of contacts, and then how does that change with respect to the strain or with respect to the density that you are having? So what would you
Nirmal and
expect?
Shiva, can we drag it down to
So
little
it's
later?
my it's my talk now.
Yeah.
Yeah.
Basically, you are
Absolutely.
taking time out from yours.
No, that's not good. Okay, let's catch it later.
Yeah, let's catch it in the
Sure.
break room.
Okay, great.
Thanks.
So now it's a great pleasure to welcome Shiva. So apart from the formal introduction, I mean, yeah, we had a long overlap many times, but yeah, let's do that first. So Shiva had a PhD from IISc Bangalore in 2014, Shiva Surendra Chandran. And before that, he has MSc from Anna University, and then BSc also from Vellore. And he was a postdoc. He started a postdoc in University of Freiburg, which is the same group where I did my PhD. And there he quickly transformed into a research project leader, doing very successful work. After that, he had a little brief stay as a postdoc in Tübingen, also in polymer and soft matter physics. So what I know, he is interested in soft materials, especially polymers, and sort of questions related to non-equilibriums. So Shiva, the floor is yours. Take it away.
Okay, thank you. Thank you, Midun, and thanks Sunita and other organizers for giving this wonderful opportunity to discuss about my work. And so I'm Shiva Surendra Chandran. I recently started my position here in Kanpur, which is not quite recent, it's like a year now. And here we started a group focusing on the non-equilibrium phenomena in soft and biological matter. So, and that, of course, starting a group starts with having a team, and that's the team of students. So Pankaj is focusing on non-equilibrium phenomena observed in polymer films, and Hemlata is another PhD student who is focusing on non-equilibrium phenomena observed in bacterial biofilms, like collective behavior and pattern formation and so on. And Manish is a master student from IISER Pune, who is also doing work on biofilm formation and swarming. And then, of course, we do collaborate a lot, both in-house and outside. So I, with Krishna in physics of IIT Kanpur, and with Saravanan in biological sciences and biological engineering department, where who provides us the bacteria, and with Jaideep in IISc Bangalore. So broadly, there are two different kinds of non-equilibrium that we are interested in. One is a driven non-equilibrium system, where we are mostly focusing on material systems and trying to subject them with restricting potentials, or subjecting them with flow, and looking at phase transitions at the metastable zones and so on. So here we broadly focus on three different directions, like starting from nanoparticle membranes, where we explicitly try controlling the the relative contributions of entropy of the polymer chains, and the enthalpy, that is the interaction of this polymer chains with respect to with the matrix or with the particles and so on. And then this has a lot of applications which I'm not going into. And then we also look into pattern formation, including crystallization in polymers and also in other systems. And here what you see is beautiful patterns formed by this mundane polymers called polystyrene, the same materials which are used in your styrofoams that are used in packaging. And then we also, do a lot on looking at polymers in complex flow dimensions and looking at the response. And this is one of the main thing that which I'll discuss today. And then also of late we started with Krishna here, looking at slip liquid infused substrates, and looking at the deweighting and electroweighting phenomena of these droplets in such substrates. And then there is another major direction which we take is also systems which are intrinsically in non-equilibrium. That is with biofilms and looking at their structure formation dynamics at across multiple scales, starting from these are just photographs taken out of simple mobile camera, and then you can see this kind of wrinkling pattern, and this wrinkling can be associated, or you can try learning or understanding such wrinkling pattern via this buckling instabilities and so on. And then we also look at the spreading of bacteria on a substrate, and which is what your this GIF image captures here. And then this bacteria, because of their geometry, they also arranged in nematic forms, and then you can also associate it with nematic, you also get topological defects. And we also are interested in looking at the emergence of such topological defects and their importance in structure formation essentially. And then we also look at this is a short stint that I was with Frank in Tübingen, and where we looked into liquid phase separation in biological systems. And there we look at the structure formation and dynamics at in situ in real time. And for doing all these things, we of course experimental groups, so we rely on a lot of experimental methods, ranging from X-rays, be it in-house or large-scale facilities like synchrotron. So we do use X-rays to look at both structure formation and dynamics across length scales, using both X-ray photon correlation spectroscopy and X-ray free electron laser. And then we also use microscopy, AFM. Apart from using simple imaging, we also use AFM as a tool to measure the local spatio-temporal variations in the rheological properties of various soft systems. And then we also use rather straightforward optical microscopy based techniques again to follow the fluid flows and pattern formation and so on in situ. And of all these things, today what I'll focus on is possibly the simplest of all these techniques here, which is optical microscope, and we'll focus on the driven non-equilibrium behavior in polymers. And the essential idea here is to convey that even the simplest techniques can provide significant scientific insights into non-equilibrium problems that you are having in hand. And this is a work that I've done as a research project leader in University of Freiburg. I was using the lab space of Gunter Reiter, and we also have a lot of interactions and so on. And then this is my student Rishabh Handa, who's currently doing PhD in Christian Wagner's group in Saarland. And so most of the work that the first part of the slides is essentially performed by him, and then of course I was performing experiments in some simple theory. Okay, so let's get into the work. Let's get into polymers. So polymers, as we all know, are long chain-like molecules, right? And if we think of neutral polymers, interestingly, all the hydrodynamic interactions are screened within the size of a single monomer. So what do we mean by that? We say that all energetics are completely removed from the system, and you're essentially thinking about some coil-like system, and whose equilibrium structure is going to be determined only by the number of accessible conformational states that the system is having. That is, entropy decides their equilibrium structure. Right, and now we can easily show that the maximum number of conformational states can be achieved if a polymer is made to follow a simple random walk statistics. Okay, and random walk by definition is not a space filling structure. So in a polymer melt, there are many polymer chains which are interpenetrating within the envelope volume of a single chain, as I've shown here with the darker green and the lighter green background. So within the envelope volume of a single chain, there are many polymers which are interpenetrating, and there are no interactions, as I already told you. But because of just the mere physical presence of so many polymers within the envelope volume of a single chain, this manifests into enormously long relaxation times for polymers. When I'm saying relaxation time, I'm speaking about, for example, the self-diffusion time of a polymer, right? And also it gives rise to the interesting viscoelastic properties of these systems. That's in equilibrium. So where we have, very good understanding of these systems and so on. But in reality, polymers are often subjected to intense flow fields. For example, in industrial processing conditions, or even in biological level, like for example, when you're creating DNA and thinking about protein translocations and so on. So these are all subjected to intense flow fields or intense geometrical restrictions, where polymers stretch and align with respect to the flow field direction, as I'm shown here. So clearly, in such situations, the randomness is lost. Right? So the polymers adopt non-equilibrium molecular conformations. So at the at the scientific level, this is already taking the system into a completely new arena, and where there are no governing principles which describes how the properties of polymers which are non-equilibrated changes and so on. And at the technological level, you still can ask, like, okay, why should one worry about? One has to worry about that, because if you think, for example, a simple polyethylene carry bag like that you are using for getting these grocery items. So the modulus of such a polyethylene in equilibrated coil fashion, that has like something of the order of 1 gigapascal, right? And now if you manage to stretch 90% of the polymer chains in that grocery bags, and then make a structure out of that, then the elastic modulus increases to as high as 250 gigapascal, right? So this is excellent. Now you can use the same material which was used in grocery bags to make ropes for towing ships, to even forming bulletproof vests and so on. But what is the reason behind such enormous increase in the elastic modulus? Enormous change in the properties, right? We don't know the reason, and unfortunately, we rather rely on empirical relations and trial and error approach in order to control these deviations and properties. So in that situation, we were asking, okay, if this gives such enormous application potential, can we predict the relation between processing and property, and then think about what is the possible molecular reasons for such enhancement in properties? So to do that, we chose polymer films as our model systems. And the idea is essentially that we want to make polymer films which contains stretched or coils which are in non-equilibrium, adopting non-equilibrium conformations, and that we do just via usual spin coating, where essentially the rapid evaporation of solvent freezes polymers in non-equilibrium conformations, and this freezing also introduces lot of stresses in plane, which we define as residual stresses. So the idea is straightforward, that we want to control the evaporation time or the preparation time, and then measure the consequences, that is the residual stresses or the time that it takes to relax. Okay, and for that we chose a system like polystyrene, which for all practical purposes is nothing new to be understood about this polymer at the chemistry perspective, and that's the reason why we chose this as a model system. And we just want to see like how our preparation pathways, that is changes in the preparation time, controls the non-equilibrium property, which we define it via the residual stresses, which one may loosely define as the order parameter which defines the deviation from equilibrium. Okay. So for now we are having polymer films, and we want to look at their properties, and hence we have to now think about methods which are non-conventional, and the method that we have relied on is the straightforward approach of deviating, which Mithun briefly introduced, but just for the sake of completeness, let me describe the process of deviating. So basically the idea is that you take a substrate and you coat the polymer film on a substrate which it doesn't like. So you just coat it and then freeze it there, and then you give them energy, then it wants to retract from the surface, and the retraction can also happen in the form of nucleation and growth of holes. And this is something that you can easily look at in situ and in real time by just putting this the whole polymer film setup in below the optical microscope, and that's something that what you are seeing. Now if you think about the physics of these systems, the growth of these holes, so these are well understood, and these are essentially when I said unfavorable substrate, basically means the capillary stresses are the spreading parameter which defines the favorability. So the capillaries, the unfavorability, that is the spreading parameter, drives the polymer to move away from the substrate, and of course the viscous forces are going to balance this capillary force. This is for a system, you don't have to be polymer, it can be for any fluid system that you can think of, right? But now if you have polymers, and especially those polymer films that we have created which has a lot of residual stresses, which then introduces an additional driving term, which is a time dependent term, which is because of the residual stress. And why is it time dependent? Because any non-equilibrium system with time is going to look for explore towards equilibrium, and hence the stress is possibly going to decrease, and that's why we have additional time dependent driving force. This is all the idea that I'm going to use for the rest of the slide in terms of the methodology. Okay, so now let's look into the results. So what I'm going to show you now is polymer film of a given thickness. Thickness essentially defines your order parameter in equilibrium. So if the thickness is constant, then all physical properties are expected to be constant, right? That's the reason why we just take one thickness. And also we are having thickness of 90 nanometer, which for the people within the community knows that these are already thick enough that you expect bulk like properties, right? So you don't expect any confinement induced properties. And we keep the film at a given temperature which is much above the glass transition temperature. That is, now these films are expected to be fluid, right? And they can just flow. And we just waited for 400 seconds. And so this is just the molecular weight, which is just for the reference for people who are interested. So here I'm just showing you snapshots of two films which are having exactly same film thickness, as you can see it from the background color of the film. And the only difference is that one is prepared at a very slow rate and another is prepared at a very fast rate. Right, the film which is prepared at a fast rate, you can clearly see that you have many number of holes, and they are also grown for larger distances. So for films which are prepared faster, we can expect that, okay, so you're deviating further away from equilibrium. So in our definition, we would expect larger residual stresses. So this residual stresses, one may imagine as a contribution to reduce the barrier for nucleation of hole, and that's why you have more number of holes. And also, it adds up to the driving force, and that's why the holes are much bigger than in the films which are prepared slower. Okay, and now to understand this further, we just exploited the fact that this nucleation of these holes are random. Okay, so they nucleate after different delay times, and now if you can follow the velocity of these holes which are nucleated after different delay times, so then you would expect the stress contribution to decay with time, right? So that's exactly what I'm plotting here, that the initial deviating velocity of these holes which are nucleated after different delay times, that is the ones which are nucleated at 0 time in this scale, would mean that it contained all the residual stresses which are stored during the preparation, and which after infinite waiting time, then you would have expected all the stresses to relax. Okay, and here I plotted it in a semi-logarithmic fashion, and looking at the dependence, we can just fit it with a simple exponential behavior. So this was quite surprising for us, because we were not expecting a simple exponential behavior. We were rather expecting one could have multi modes of relaxation and so on so forth, and you'd rather expect a stretched exponential or maybe a power law like relaxation or something, but we saw a simple exponential relaxation which allowed us to extract the characteristic time for the relaxation of these stresses. Okay, and then you can also notice that, like, the dynamic range of the relaxation, that is the velocity at time t equal to 0 in comparison with the constant velocity is much larger for films which are prepared faster than the films which are prepared slower. And then just by using a simple scaling, that, like, at in the constant velocity is what is expected because of constant film thickness, so the constant capillary stress, and then whatever additional is coming is because of the residual stresses that we have introduced during spin coating, during preparation, right? And by just doing such a simple scaling, and we know everything else, we know the spreading parameter, we know the film thickness and so on, so we can get the exact residual stress. And you can clearly see for films which are prepared in different ways of exactly same film thickness can contain residual stresses which are orders of magnitude, one order of magnitude different, right? And the relaxation times are correspondingly slower when your stresses are larger, which indicates that you are in the nonlinear regime of the rheological behavior of these polymers, right? So then what we did is, like, we want to understand this further. So then we just thought, okay, when we say that the residual stresses are introduced because of the rapid evaporation of solvent, right? So when we say rapid evaporation of solvent, it basically invokes two different time scales. One is the time that a polymer wants to equilibrate itself from any mechanical perturbation that it experiences, and another that the time which is available during the preparation. If the time which is available is lesser, so then the polymer cannot relax. Okay, so you essentially need two different time scales. So in terms of the time available during preparation is something that we can just solve a simple rate theory, and we can get the total time needed to get a polymer film of dry melt without any solvent, starting from a simple solution, right? So which based on the evaporation rate of the solvent and the rotation rate that you have used for spin coating and the kinematic viscosity, which of course depends on the dynamic viscosity, right? And now this is a theory which was developed for really simple small molecules, but with polymers we know that the dynamic viscosity also depends quite significantly on the concentration that you are using, right? Whether it is just touching, then it will still have like more like a small molecule like behavior, but then the moment it starts coming together and starts entangling, so then you will have a divergence of the relaxation time, and then we just put this in here, and then we would get the actual time which is available for the preparation of the polymer films. And what is the time that is required for the polymers? That is something that we don't know, and there are no theories currently which allows us to think about it, right? Because now you are thinking about polymers which are now subjected to an environment which is always changing, right? So the concentration is always changing, so which means that relaxation time is always changing. So we don't know what is the molecular weight dependencies, and what is the nature of the relaxation and so on. So to understand that, what we did is just we took a polymer, we made polymer films out of polymers of different molecular weight, and then obtained exactly same film thickness, but we only varied the preparation time controllably, and that's exactly what I'm showing you here. The film thickness is fixed, it's 15 nanometer, and the temperature at which it is deviating, it's fixed, so that's also clear. So the only difference which is coming is the residual stress, and that's what I plot here. The residual stress is plotted as a function of the preparation rate. So higher the rate, you expect the films to deviate further apart from equilibrium, and hence the residual stresses should increase, and that's what you're seeing here, right? And then if you see at a given preparation rate, films with higher molecular weight departs further out of equilibrium than the films which are formed of lower molecular weight. Okay. And then what we did is we just did a arbitrary scaling so that all the data can just collapse with the lowest molecular weight, and you get such a beautiful dependence. And this scaling allowed us to identify what should be the molecular weight dependence of the equilibration of the time that a polymer needs to equilibrate in this thing. And this has a dependence of n to the 0.3, which we have some rough ideas of what could be the reason, but it's not yet clear. Okay. And then what this allowed us to identify is that we can now define dimensionless preparation parameter, which allows us to look at the preparation pathways stuff. So then what I've shown you here is that now these are films which are prepared in completely different pathways of similar film thicknesses, and all of them just collapses into a single master plot of given slopes, which are all plotted in double logarithmic plots. And then, the slopes essentially gives you the exponent. And, this is this preparation parameter that we have identified beautifully, captures the deviations from equilibrium. And now we even have, since the exponent is like more or less defined, now we can say that, like, if you want a film with a given residual stress, how much, what should be the preparation parameter that you can choose? And so how you have to prepare the film in order to get a given stress that you want. So that's why we say we have achieved a predictive ability in this system. And now all these experiments are done in Freiburg in Germany. Me and my student has performed these experiments. And then interestingly, our collaborators in France performed similar experiments. And again, you get exactly same exponents, which says that we are actually looking at some universality in the behavior now, where we have we one, that preparation parameter essentially allows us to predict the non-equilibrium behavior of polymer films, and two, what's the reason behind these scaling exponents, which we have now understood much better than before. But I think for the sake of time, I'm just going to skip the remaining part, and I just go to the conclusion. But I think if I would have possibly convinced you that, like, the time that you're giving the polymer during preparation matters. And if you take care of this time, then this allows you to quantitatively correlate these polymers. And this second point is what I've now skipped, but we could also show, like, what are the microscopic reasons why we have such deviations in properties. And from a technological perspective, one can now say that, since we have now such a control over preparation time, we can also get materials of tunable properties and performance, and we don't need changes in chemistry anymore. All that we need is just differences in preparation pathways. Right. So with that, I'll just thank you, and I'll also leave you with a message that what we believe in, that with polymers, with equilibrium, like random coil-like conformation, we think that we only witness the tip of the iceberg, and with non-equilibrium, there is so much is remaining, and it to be found, and there could be a lot of rich physics which is still remaining. Okay, with that, I thank you.
Okay, thank you, Shiva. Excellent talk. So we have about 3-4 minutes to discuss. The talk is open for any question. Please go ahead. So Sunita has a question.
Yes.
A very nice talk, Shiva.
Thank you.
I was wondering, you mentioned about this entanglement length scales and also the dynamics, right? The time scales.
Yes.
Is there a normalization one can think of from the tuning experimental parameter point of view? Like H versus thickness is one parameter in that way we think, right? So I just assume that the molecular weight that you showed in your slides are much smaller than the thickness of the film for the entanglement to occur. Am I right? No. Okay.
So these are all already thick enough so that, like, you expect. So these films now, like, for example, you have like 100 nanometer. Even we did this experiment at, like, as thick as like 400 nanometer. So it's not the thickness which decides. I mean, of course, you're right that, like, thickness can also restrict the system from entangling. But then these are already, like, so thick that you wouldn't expect thickness to be an important parameter, right? And now we are in principle.
So what is the sorry to interrupt? What is the size of the polymer chains here?
So here it is okay. So if you want it in nanometer, so then these are like something like 7 nanometer. So for this, the molecular weight is like 524. In melt, you expect it to be something 7-8 nanometer.
Okay, so what promotes the entanglement when you have such a smaller polymer size and the thickness of the film is big enough? So is the so first thing is what promotes the entanglement, and the second question is that is there a gradient of this polymer chain density if you move away from the substrate to the bulk air polymer interface, if I can say that?
Okay, so I'll take the first question to start with. So what promotes the entanglement? So these chains are already long enough that if you just look from the random walk statistics, so that you need to have entanglement for having any stable polymeric product out of these systems, right? So now the threshold molecular weight for entanglements to occur for polystyrene is at 18 kilogram per mole. Okay, and we are at 550 kilogram per mole. So we are well away from the threshold molecular weight, and hence these systems are expected to be entangled.
That's
And
for the
now,
bulk, right?
that's in bulk, and like that's in dry melt state. Okay, and now we are just preparing the dry melt state in such a way that we are not allowing all this polymer, giving not enough time for these polymers, that they want to entangle, but they are not completely entangling, so they're only entangling partially. That creates this kind of a tension in plane, and that's what we define as residual stresses. So that's point number one, right? And your second question, what was that?
The second question was that can you correlate again the age versus the size of the polymer with the dynamic, the time scale that you're talking about the entanglement?
Right.
So
We can,
Sunita,
yeah.
I mean, we have just touched the time limit. I mean, since we are like, we can go into breakout room. Can you carry that one there? Because I'm also getting a student question. I don't know how much that could be done in a minute. Is there?
So please
Mithun?
take up the student question.
Yeah. Mithun, are you there? Mithun calling Mithun.
Hello, sir. Can you hear me?
Yes,
Yeah.
Mithun.
Yeah.
Hi, sir. The talk was really nice. Sir, I have one doubt regarding the talk. Sir, so you have varied the spin speed of while preparing the film, right, sir?
Yes.
So, sir, what about how much did you keep in this acceleration?
So acceleration is important. That has to go in par with the spin speed. Right?
So, so for initially for if you so you varied the time accordingly.
So I keep both the acceleration and the spin speed to be similar. So that allows me to like think of the system in a yeah, like yeah, that reduces other problems which are possibly coming in.
Okay, sir. Okay, sir. So I had this doubt because like if you're going for very high RPM, like 12,000 RPM, and if normally for if 2000 RPM, we keep around 2 seconds for acceleration or something. So that acceleration will be around 1000 RPM per second.
Sure.
So if we go to 12,000 RPM for making the film, so now for 12,000 RPM, it will take 12 seconds. So
yeah, but I don't do that, because if you give 12 seconds for the polymers to already do what they want to do, so then you are not actually driving them out of equilibrium. So
no, but this, yeah. But for keeping similar acceleration, we'll have to increase the time accordingly, no, sir?
Exactly.
So
decrease in that, in your case.
Yeah, in my case, decreasing the time.
Yeah.
So, so what we are seeing as residual stress is it the effect of increased acceleration for getting the high RPM, or?
That's a good question. Now, right after this initial acceleration, if your polymer still contains like more than 50% of the solvent, so then you would expect that the acceleration is not actually the factor that you have to look for, right? Because the polymer is still fluid, and the moment you cross that you get into the glassy fraction, so then you have driving out of equilibrium, and hence the rate is what we think is the main parameter that one has to think about.
Okay, sir.
Okay, Mithun and Siva. So I think we can have one-to-one meeting later. So we are already 2-3 minutes late. So thanks again, Shiva.
Thank
so
you.
Our next speaker I can see is Dr. Ravindra Pandey. Dr. Pandey, are you there? Yeah. Okay, perfect. So let me introduce him. So Dr. Pandey did his PhD in physical chemistry from IISc Bangalore. Then he did a postdoc in several places, Max Planck Polymer in Mainz, then UT Austin. And he was a faculty fellow for 2 years in the ISCS Kolkata. And now he's an assistant professor from 2018 in IIT Roorkee. His area of interest is probing structure and dynamics at surfaces with ultra-fast nonlinear spectroscopy, charge transfer at organic heterojunction interfaces, and interfacial structure of ionic liquids. So he also awarded e-SMYIM Duo Award and Ramanujan Fellowship since 2017. So Dr. Pandey today will be talking about probing structure and dynamics at complex interfaces. So the floor is yours, Akshay Pandey. Please go ahead.
I hope everyone can hear me.
Yes, we can.
Great. Thank you, Dr. Mithun, for the kind introduction. And thank you, Dr. Sunita, for the invitation to give a talk in this symposium. So what I'm going to talk today is that how one can probe structure and dynamics at interfaces. So in our group, we try to probe different kind of interfaces, but here I have primarily focused my talk on some small on biological surfaces, and particularly we are going to probe water. But the first question is that why we have to probe surface interfaces, right? The answer is rather simple. I'm a chemist. So if I talk about a very simple process that is called catalysis, that molecules comes and sit on the catalyst, and depending on the orientation of the molecule on the surface, the efficiency of the catalyst is going to be entirely different. If I go to a more complex process like protein-water interaction or membrane-protein interaction, which has a quite importance in biomedical application, all the action in such case also takes place in the region where the protein meets with the membrane or the water meets with the membrane. If I talk about the modern devices, such as organic photovoltaic cells, that all the charge separation takes place at the interface. And depending on the efficiency of how the charge is separating at the interface, that dictate the efficiency of the device. So if I have to understand all these processes very well, I should have interface-specific molecular level information. But the question is that probing interface is a challenge. Why it is a challenge? Let me give you a very simple example of water. And this is a kind of water. You can assume this water in a glass or something. And if I want to probe the structure of this water, what I can do that I can simply do a simple IR spectroscopy, and I can get the information about that what is the my structure of water. And from our BSc level chemistry, we all know that if I take a IR spectrum of this water, I'll get a broad spectrum of the water, and it is because the water has different kind of hydrogen bonding. But look at the water-air interface. At this water-air interface, some of the OH bonds are coming out from the surface. And these are not that much tightly hydrogen bonded compared to the water which are present in the bulk. And if that is true, I should have a signal somewhere here, which should be very narrow, and that signal should match with the gas phase water. But I cannot see that signal here. The reason I cannot see that signal here, because the bulk water molecules are so many in numbers that the very tiny signal which is present at the interface get lost. So if we have to probe these interfaces, if I want to probe this water molecule, which are present in the interface and doing most of the action in case of any biological system, we need a technique that can separate the interfacial signal with the bulk. That is where the sum frequency generation spectroscopy comes into picture. So in this spectroscopy, we come with a resonance beam, which excites the water molecule or whatever the vibration that you are interested in. Then you come with a non-resonance beam. And when these two beams comes together, you get a beautiful signal from the interface, which is the sum frequency of IR plus visible. And the beauty of this technique is that if you go into the bulk, the signal disappears. To understand that why the signal disappears, we have to understand a little bit of fundamental of nonlinear optics. So when I am doing my nonlinear second order measurements, essentially it is guided by two electric field interacting, connected with the chi2, giving me the net signal. But if I have a center of symmetry that is mostly present in the bulk, then what happens that since electric field is a kind of vector, I can just simply change the sign, and my net signal is also a kind of vector, I can change the sign. Then I get a kind of relationship between P2 is equal to minus P2. That is not possible at all. So that relationship will only valid if this chi2 property has to be equal to 0. And that is why in the bulk, since the chi2 is equal to 0, I don't see any SFG signal, while at the interface, I see the signal because the symmetry is essentially breaking. Just few minutes back, I have shown you a vibrant spectrum bulk water. And I have mentioned that point that if I have to probe interface, then I should see a narrow peak somewhere here. Now let's try to take the same spectra of water with the help of vibration some frequency generation measurement. Boom. You can see that what I was talking about, the narrow peak, which is due to this free OHs, generally that is called in the literature. It means that they are not strongly hydrogen bonded. It appears, plus you get the bulk water, interfacial water signal also. So I hope this example is good enough to convince all of you the potential of some frequency generation measurement to probe surfaces and interfaces. Now let's go to an actual problem. So this is the problem which I have done in Max Planck, and that is about the ice nucleating protein. As the name suggests, that this protein has the property to nucleate ice. But how they do it so efficiently? That was the question, and that was the question that we would like to answer at that time. And I hope by the half of my talk, I would be able to answer that question. So the source of these ice nucleating protein is the bacteria. These are called Pseudomonas syringe. And in the outer cell membrane of these bacteria, these ice nucleating protein sits. And during the winter, when the temperature reaches close to freezing point, they start forming such kind of ice pattern in the leaves so that they can rupture the cell membrane and can get the food. And because of that, there's a huge loss in the crops. In fact, during your winters, I'm not sure whether you have seen in Bombay or not, but in this hilly region where I am there during winters, early morning you will see these kind of ice formation on the leaves or on the plants. That is because of the presence of the ice nucleating protein. In fact, in Sochi Olympics in 2014, the temperature was pretty high and there was not enough ice to conduct the Winter Olympics. So this Olympic committee, what they have done that they have used these pumps and these injected these bacteria in the atmosphere so that they can make more ice. In fact, they are 30% more efficient. Not only this, it has been found that some of the ice nucleating protein which are present in the Amazon forest, their presence has been observed in the other part of the world also. And so there are a lot of research going on where people believe that these ice nucleating protein, they also control the weather pattern. So what is known about ice nucleating protein? So it's a membrane protein, and generally, if you kind of look at the old papers, what is known that this protein has a kind of these amino acid repetitive unit. And if you give a look on these amino acid, these are the serine and threonine, which have the OH group present, which can interact with the water molecule and forms a kind of trap the water molecule on the surface, something like this, like the way we observe in the formation of crystal growth. And once these water molecules are arranged, they are arranged with the basal plane of the ice. And on top of that, the water molecule comes and start forming the ice. So if you look at that picture, I have membrane protein and that is interacting with the water molecule. So it's a kind of very excellent system to probe with the help of some frequency generation spectroscopy to get interface specific and molecular level information. So what we did, that we have taken a turf and in that turf we have put water. Here, instead of water, we have used D2O because to excite the water molecule, we have the energy in this range that is available, though no other reason. And nothing is going to change. Everything will remain as long as it is true for the water. The only thing is that because hydrogen has been substituted by deuterium. So all the frequency will be shifted toward the lower wave number. That's all. Nothing is going to change other than that. So this is the water spectra, D2O. And then in this water surface, we injected our isonucleic protein. And when we injected this isonucleic protein, this is what we observed. You can see that my water is more ordered now. And since the water is more ordered, therefore the intensity has been increased. Plus, I can see that the protein molecule has some kind of CH bonds are there. So the signature of the CH vibration is also there. So this is, though this graph, those who are not working on SFG looks pretty appealing, but let me tell you that if you add any protein or any charge on the water surface, you will get the exactly similar kind of pattern. But the interesting part is that these isonucleic proteins, they activate themselves when the temperature goes close to the freezing of the water. So what we did, that we have cooled down our turf from 22 to 15 degrees Celsius, 15 to 10 degrees Celsius, and 10 to 5 degrees Celsius. And you can see that as we are going from 22 degrees Celsius to 5 degrees Celsius, this water is known as strongly hydrogen bonded water, which is responsible for the formation of ice. And this water is known as liquid-like water, which is formation of, water kind of stuff. And that's a gas phase water. So give a look here. When I'm at room temperature, my intensity was more or less equal of the strongly hydrogen bonded water molecule and the liquid and the weakly hydrogen bonded water molecule. But when I have gone to 5 degrees Celsius, please keep in mind the 4 degrees Celsius is the freezing point of D2O. So if you have a spectroscopy eye, you can clearly see that in my system, there is a more strongly hydrogen bonded water molecule has been formed. Perfectly fine. That's what it is, one of the requirements when the ice formation takes place. But does it happen with isonucleic protein only, or it's a kind of general behavior? So we have done several control experiments for that. But one thing is clear, that when we are decreasing the temperature, the strongly hydrogen bonded are more ordered. Then we have taken the fragment from which researchers believe that these are the repetitive units which are responsible for the formation of ice. But these are simply fragment. These are not actual protein. So what we have observed, we have not observed any change going from the room temperature to 5 degrees Celsius. We have extracted the membrane protein, the protein part from there, and we try to perform the experiment again. We have not observed any such kind of change. And that has to be expected, because once the protein is taken from the membrane, it loses its activity. Then we have performed one experiment with a very stable protein that is called lysozyme. And in that case also, we have not observed any change. And finally, we performed one experiment with only with the lipid membrane. There we have observed some change, but the magnitude was not as much as strong as we have observed for the proteins. Plus, we also observed that there is an increase in the CH intensities. So what we can conclude from there very safely, that whatever we are observing here, it's a pure effect, exclusive effect of isonucleic protein. And whatever the increase in the CH intensity, it may be because of the presence of membrane. And it is well known that when you decrease the temperature, the CHs are kind of more ordered, and it is expected to have more intensity there. Perfectly fine. So we set the first criteria. The second criteria is that the energy that you are giving to the water molecule, that should dissipate into a medium for the more formation of ice. So for that, we have performed the time resolved measurements. So this is what we do in a static SFG measurement, just we have seen a few minutes back. In time resolved measurement, you come with a narrow beam and you excite some of the water molecule to the high energy state. And when these water molecules return back to the ground state, then your signal kind of reappears. All right. So I turn on my pump beam, which means that I'm turning on my IR beam. There will be some drop in the SFG intensity because now I have less number of molecule. And as the time progresses, the signal will recover back. And this gives me the information about my system, that how the energy is going from one side to the other side. Okay, so there's a little bit off. Okay, no problem. So what we have done, we have excited, we have done a lot of experiments, but what I'm showing you here is that what makes sense. So what we have done, that we excited the weakly hydrogen bonded water molecule. And if these hydrogen bonded molecule which are sitting here, they are not coupled with the strongly hydrogen bonded water molecule, which means that they won't talk with each other. If that is the case, if I excite this water molecule, these water molecules come back to the same ground state. But if somehow the strongly hydrogen bonded water molecules are coupled with the weakly hydrogen bonded water molecules, then they can transfer the energy to each other. It's something like that. If you are two good friends, if I ask you the money, and if he is my very good friend, he will borrow, he will easily give me that money. But if I ask to a stranger to give me the money, he won't give me the money. That's what I'm trying to say here. Because these two, they do understand each other so well that they start exchanging the energy. So let's see what happens. So what we did, that we excited the weakly hydrogen bonded water molecule here, and in no time, the energy has been gone to the strongly hydrogen bonded water molecule. So let's try to see what happened in the case of water. So in the case of water, these weakly hydrogen bonded molecules are coupled, but not as strong as the presence of ice-neutering protein is doing. So one can pull out that information by using various kinetic model. And what we found, that in case of D2O, it takes 100 femtosecond to release that energy, while in case of ice-neutering protein, if it is present, it does in just 150 femtoseconds. Just a cartoonic picture to explain what I'm trying to tell, that I'm exciting the weakly hydrogen bonded water molecule, but within no time, the energy has been transferred to the strongly hydrogen bonded water molecule. And that is how it is helping, it is removing the heat from the surface and helping in the formation of ice. So what we have learned, that's a famous cartoon character, Marvel comic cartoon character named Iceman. It kills its enemies by forming the ice. And it uses these ice-neutering bacteria to kill these enemies, his enemies. So what we have learned, that there are some kind of particular bacteria, and which in their surface, they have the ice-neutering protein. They control the molecular structure, energy transfer of the interfacial water. And it does so by ordering the water at the close to freezing temperature. And the freezing transition is further enhanced by effectively removal of energy from the nucleation site. So this is the first part of my talk. And this is the second part. In my second part of my talk, this is the work which has been done at IIT Roorkee. And what we are going to show you, that how the interfacial water changes in the presence of different type of charged nanoparticles. Why it is important? Because these kind of gold nanoparticles, which has been, protected by the different kind of ligands, these are very nowadays are used for the drugs carrier, or for the kind of fluorescent molecule to detect the cancer and the kind of stuff by the heat therapy kind of stuff. So we want to see that how the interfacial water changes, and does the interfacial water play any role in when such kind of interaction changes. So what we have done, we have used the different kind of model membrane, such as DPPG, DPTAP, and DPPC. The reason for choosing this kind of model system is that, for example, if I take DPPG, it has a negative charge. So it provides the negative charge at the interface. If I take DPTAP, it provides the positive charge at the interface. And if I take DPPC, due to the presence of positive and negative charge, the net charge at the surface will be kind of zero. And then what we can do, that we can interact them with the anionic gold nanoparticle and cationic gold nanoparticle and try to see that what exactly happened. The idea is the electrostatic will play a role. And if I have a negatively charged nanoparticle that is interacting with my negatively charged membrane, it will repel it. So I should not see any effect. So let's see whether it is true or not. So what are the possible scenarios? So there may be possibility that the water molecule, when you are putting a charge, opposite charge, the nanoparticles, they can come to the surface and they can repel some of the water molecule without changing the structure of the water. If that is the case, then we'll observe that the line shape will remain the same, but there's a drop in the intensity. Or it may be possible that when the nanoparticle is interacting with them, then the water structure changes. And if the water structure changes, then my nature of the line shape will change. So that will give me the idea that my water structure is completely changed. Or it may be possible that it simply removes some of the water molecule from the surface. In that case also, we will see that there is a only drop in the intensity. So what we have done, that we started with we have taken the water in a trough, and then we injected our DPPG so that they will come to the surface and make a perfect monolayer. And when that is happening, we can what will happen that because of the presence of the charge, the water molecule will reorient themselves. And since H has some positive charge, so it is kind of assumed that H is coming to the surface. And that can be monitored with the help of surface pressure. As you add your DPPG monolayer, you will see that your surface pressure will also increase. And then you can collect the spectra like the way we have done before. And this is the DPPG spectra without the presence of any gold nanoparticle. Perfectly fine. Now the idea is, I have already discussed that this is a strongly hydrobonded water molecule and that is the weakly hydrobonded water molecule. So the idea is to inject the gold nanoparticle beneath the layer and see what happens. So what we have done, that we have added the anionic gold nanoparticle, which means that in the gold particle surface, there's negative charges there. So our expectation is that negative will push the negative charge, and you should not see any change in spectra. So this is what our expectation. And when we have performed the spectra, when we have performed the surface pressure measurement, we have not observed any change in surface pressure, which means that these nanoparticles are not coming to the surface. If they are coming to the surface, I will see some kind of surface pressure change. And then we have collected our SFG spectra. And you can see that the black one is the DPPG spectra of water spectra without the gold nanoparticles. And when I have added the anionic gold nanoparticle, more or less my intensity remains the same. So this tells me that my hypothesis, what I'm saying, is correct. And these nanoparticles are not coming to the surface. All right, now let's try to see what happens in the case of cationic gold nanoparticles. So similar experiment has been performed. And now it is expected that some of the water molecule will be replaced because of the strong interaction, electrostatic interaction between the negative charge lipid and the positively charged gold nanoparticles. So you can see that when the nanoparticle were injected, you can see that there is again increase in the surface pressure, which is confirming to me that these nanoparticles are coming to the surface. And that's perfectly fine. Some of the water molecule has been completely, the structure of the water molecule has been changed. And you can see that my water structure is entirely different compared to the previous case, which means that our hypothesis is perfectly fine. Now let's go to the positive charge nanoparticle. That's an interesting one. So if that hypothesis is correct, we should observe the similar kind of effect here also. But interestingly, what we have observed here, that when we have injected the gold nanoparticles, negative one, we expect that they will be attracted toward the surface and my signal will drop. Perfectly fine. Because this is exactly the scenario, opposite case that what we have seen few minutes back. But what happened in the case of cationic gold nanoparticles? In case of cationic nanoparticles, I do expect that they will repel each other and my water structure should not change at all. Right? Perfectly fine. But in that case, again, we have observed there's a drop in the intensity. And we are puzzled. First, we thought that we are doing some mistake in our measurements, but later we found that it's not the electrostatic, but it's the stun layer that is changing under the water. And when we are using the cationic, when we are using DPPG, it's a Na plus. Na plus is a small cation, and that is kind of very strongly hydrolyzed by the water molecule and does not come to the surface and screen the charge, while Cl negative does not do that much so efficiently. So it's not the charge, but it's the nature of the stun layer which dictate the SFG intensity, and one has to be very careful and considering these kind of anions which are also present in the system. All right. Similarly, we have performed the experiment with the DPPC, and in case of DPPC also, we have observed that the stun layer is playing a kind of role. So the similar expression can be given for that. So this was my
about to.
Yes, I'm going to finish.
Yeah,
I understand. That is why I skipped the DPPC part.
Okay.
So this was my laser lab condition in 2019. This is in April 2020. And then because of lockdown and other things, the installation cannot be completed. But now we are done. We are up and we are running. So all our setup is kind of ready. And we are working on a different kind of problems, not only this biologically important problem, but we are also trying to understand how the charge transfer takes place at the heterojunction with the help of electronic sum frequency generation measurements. We are also trying to understand that how the nature forms the functional material so nicely. And all that action also takes place at the interface. We are also interested in the protein aggregation kind of problems. And we want to understand that whether the hydrophobic, hydrophilic kind of interaction plays a role or it is governed by the electrostatic. And we are also trying to address the problem to understand the mechanism of cell-penetrating peptides. Okay, so all these processes take place at the interface, and with the help of vibration and electronic sum frequency generation measurement, we are trying to get the information about our different problems. So this is my group, and the lipid nanoparticle work was done by Preeti Gehtori. Suman and Simran, they are working on probing the charge transfer dynamics in the organic solar cells. Yogesh is working on metal organic framework and covalent organic framework. What is the role of the water? Vineet is working on the aggregation of protein on different kind of stuff. We are well funded by the IIT Roorkee. I'm extremely thankful to SERB for supporting me with the kind of funding that is required for the laser lab. And I'm also thankful to STARS for the scheme, STARS MHRD ISC Bangalore for supporting our research. Thank you all. And I would be happy to take some questions.
Okay, thank you, Dr. Pandey. It was a very nice talk. I actually found out a few interesting things. But what I suggest that if there is one and two very quick questions, let's go ahead. Otherwise, we also have breakout rooms because we are, it's like as it's my responsibility as a session. We are just like 2 minutes late, and it's like a collective responsibility starting from me. So any question, please go ahead, raise your hand. There we have time for at least 1 and 2 short ones.
Mithun, I have a question, but
Sure.
maybe I can chat
You want
in
to
the
go
break, because my question will be slightly bigger.
Okay, then I mean, if Dr. Pandey is in the
Danny, are you around?
Okay.
Yes. Yeah, so we can break out into rooms till 4:15, right? Because we have a tea break soon after this.
Right.
Then we have a lot of time, I guess.
Right.
So 3:15 to 3:45 is done now. Yeah, interaction session is 3:45 to 4. There is a tea break. So I think we have ample time. We have ample time.
Thanks, Danny.
We can even have some discussion here as well. We have ample time.
Yeah. So can I go ahead and ask my question?
Sure.
So yeah, Ravindra, really nice talk, and I enjoyed it, and I also learned about this new technique, which I believe is very useful for the interfacial measurement, right? You talked about detecting the water layer using this technique. So is it only sensitive to the vibrational mode coming from the water molecules, or like you also have a lipid? So is there a way to tune the frequency so that you can look at the...
Yes. So if you remember that when I've shown the ice nuclear protein, we have a kind of range there where we are probing the CH vibrations also. So the topaz that we are using, that decide everything. So whatever the vibration frequency that you want to probe, you can probe that one. Not only vibration frequency, what I have not talked about the electronic SFG. So you can come with a visible light. Let's say you can generate the white light, and that can be used whatever the kind of range that you want to use. For example, you can put the 800 nanometer on the cuvette, water flow cuvette, and you can generate the wavelength from, let's say, 300 nanometer to 1600 nanometers. And then you can use whatever the range that you want to use. You can probe whatever. So not only the water frequency, you can probe CH, you can probe P double bond O. So it's all depend on that. It will be a little bit difficult to probe in the deep UV region, but there are, because we are restricted by the camera, but people have done the measurement. If you have a kind of deep UV sensitive camera, you can do the measurement in that range also.
Interesting.
Yeah.
Can I ask the second question, Mithun?
Sure.
Yeah.
I also have questions. Go ahead.
Okay. Yeah. So the second question was in towards the end of your talk you told us about the stern layer and basically the change in the signal coming because of that, not because of the change in the water structure. But see, this also will depend on the size of the salt molecules that you have.
Yes,
salt
that's
ions
a
that
very
you
good
have.
question. So here we have done simple water, but I think that you can change you can put some electrolyte there and you can confirm it. We have not done that, but that is our plan, that we will change the concentration so that we can reduce the stern layer, and then we can see that whether the effect is there or not.
Yeah,
yes,
that would be very interesting actually, right? Because that's something not possible to do with at least the technique that I was familiar as of now.
That's possible, yes.
Yeah.
And one more thing I have not mentioned, that all these results were confirmed with the MD simulations. But I am not an expert of the MD simulations, so generally I try to skip it.
Okay.
Yeah.
And I see other hands being raised. So maybe
Sure. Basa has a question.
Have one. Hey, nice talk. So maybe I missed this point, but what is the lens? What is the lens scale range that you can pick up with this technique?
Yes.
Maybe I missed that point. Yeah.
Yes. No, you have not missed that point. It's a wonderful question. So it all depends on that how much charge you are putting in the surface, because what you are measuring the ordering of the water molecule. So if I have to simply, for example, if there is no charge and I'm trying to probe the water molecule, right? So usually something around 5 angstrom you measure. Okay. But if you put some lipid there, because lipid are providing some charge, so you know that if I try to plot, the electric field potential strength will go something like this.
Correct. Yeah.
Now you have more charge at this interface. If you can provide more charge at the interface, then that will also play a role. So if lipids are present there, then probably you can measure up to 15 to 20 angstrom.
Okay. Yeah.
So though I'm saying monolayer, but it's not exactly monolayer. Whatever is coming among the 5 angstrom or 15 to 20 angstrom, that you are measuring.
Sure. Okay. Yeah. Thanks so much. Yeah.
Okay. So is there any other question? Otherwise, I'll go ahead. Okay. I cannot see any raised hands, but feel free to stop and come in. But let's say I should go. So first thing, I don't know whether you realize or not. It also took a little bit time for me to figure out. We are meeting 16 years later. So you are in IIT Guwahati MSc, is that?
Yes.
Actually,
I realized that we both have put a lot of weight actually.
That's true. That's true. So it took some time to figure me out. Okay, is that? Yeah, that is. So yeah, you basically was like 1 year senior, and then I was there briefly there, then quit and came back to Calcutta. Anyway, coming back to the science. So have you already got this SFG here also set it up?
Yes.
Oh, excellent.
It's up and running. Yes.
It's excellent thing. It actually helps quite a lot to this, even our confined polymer film community.
Yep.
Yeah. And the
so
second
Ravindra,
thing,
I'm sorry to interrupt. I see you have gained a lot of collaborators, most probably.
Yeah, that's the idea of this kind of meeting, right? I mean, your chemical engineers are here, physicists are here, biologists are here. So that's why when you sent me the invitation, I really agreed it.
No, I'm very glad you accepted our invitation.
Yeah, the conformational degrees of freedom that we are interested in, SFG really picks it up.
Fix it up. It can. I mean, you see this. Who is this guy, Shiva? In Japan, this
Sasaki.
Yeah. So they have, I mean, even in our community in polymer film, from Kyushu, or I think, yeah, something
So
like
in
that.
fact,
Even,
there is in the Michigan University, there's a Professor Jen Chen. He has done these kind of measurement to find out the orientation of the polymer at the interface, and he has done a lot of studies. In fact, he has shown that this some gauge kind of structure is possible. All this kind of different kind of polymers are there.
there are many
Gauche
more.
With the help of
and
SFG,
people
he has
have
proved
found
that
these
these are the
things.
different kind of polymers are actually present at the interface. Yes,
That's true. Yeah, there are a lot of good work has been done on them and still working. Eventually, some people also tried to look into the this strain in the chain, which me and Shiva was telling, okay, whether that kind of chain also alters the interfacial structure, and
Yes.
also they used SFG.
Of course, because as the chain is, if you have a bigger chain, so the van der Waals interaction among the chain will be different, right? So that will definitely play a role. So that's
Anyway,
what I was teaching this polymer chemistry to our students, and in the yesterday's class, I taught them that why the Fleury-Huygens theory is not correct, and then why you have to take the viral equation there and you have to account for those kind of things there.
Okay,
Yes.
second virial coefficient.
No, Fleury's theory, I mean, saying that it's not correct is like understatement.
The Fleury-
Fleury-Huygens
it's correct, but it does not account for all the
it's a very limited range where it works.
Yes.
Yeah. If it is Fleury, then if it is only Fleury, then it is a pure accident which two cancelled error came up to the scaling. But if it's Fleury-Huygens, it's a separate case.
Right.
Anyway, coming back to your these ice nucleating proteins, I mean, is this something people can get commercially, or one has to synthesize it?
Well, we have used the commercial proteins,
Okay.
but there are groups in Alaska where they are getting the fish and then taking their outer surface, because that's extremely cold environment, right? And then still the fish survive there.
Good.
So they are trying to extract it from there.
You also at some point told that you were also working on the MOFs, COFs, and whatever.
Yes.
I have also started little bit with the raman, because the inspiration was from the paper by Arco in PRE.
Okay.
So I mean, what extra SFG does, which you think, like, compared to this raman setup where people already took it, carried forward earlier days?
Right. So essentially, when you do the Raman mode, right, basically you are getting a kind of bulk signal first of all, and you are measuring the polarizability. And what I have not discussed, that when you are measuring the chi2, that is nothing but the product of alpha and mu. So not only you are determining the dipole moment of your system, but you are also determining the polarizability of your system. And because these two information can be used to extract the orientation of the molecule also present in the interface. So that information, because for example, if the molecule, let's say some molecule is sitting like that, and if the dipole moment is like this and the polarizability also like that, so that will be reflected in your measurement somewhere, right? But it may be possible that some molecule has the dipole moment sitting like that, but the polarizability is something like this. So that will tell you that how the molecule are oriented at the interface also. So you can get that information extra. Not only you are getting the surface information, plus you are getting the orientation of molecule at the interface also.
Perfect. Good. I'll be in touch with you for sure, because
Great.
I have one postdoc already working in this area, but
yes,
he's mainly from the
I have advertised
side.
One position for a postdoc, but unfortunately I couldn't get it. Maybe it's a Roorkee disadvantage, because we are sitting in the in the very interior part of India. So if somebody is interested to do such kind of postdoc, please let me know. I'm very happy to hire. A little bit of experience of laser I'm looking for.
Sorry guys to interrupt. So generally we have this interaction session for independent interaction with the speakers of the session. So if we can go into the breakout room and wait for a couple of minutes or seconds and see if there are no questions from the audience, then we can definitely reassemble in one chat room and we can continue discussing.
So,
I definitely want to discuss more with you, Ravindra, about this air-water interface, but we can catch up after we've addressed the questions from the general.
Perfectly fine.
Okay, so I'm officially closing the session, and thanks to all the speakers and the organizers for sure. And I cannot see the breakout wala wo jo tha.
Okay, I think it's the time for next session, which is mini talk by the students. Ravi and Medhuvi will be chairing this session. Medhuvi, are you around? And Ravi, I can see Ravi. Ravi, can you hear me?
Hi, Smith, I can hear you.
Okay. So Ravi, we can start the mini talk sessions, Ravi, now.
Okay. Good afternoon. So the first talk in this session is by Kiran and Mithun. Kiran, are you around?
Hello, am I audible?
Yes, yes. Please.
Is my presentation visible?
Yes.
Okay. Okay, good evening to all. I'm here to present my mini talk on lignin peroxidase loaded on manganese ferrite and graphene oxide composites. We have studied its antibacterial, antioxidant, and melanin decolorization potential. As we all know that melanin is a skin pigment which is responsible for the skin and hair color. It is produced by the oxidation of amino acid tyrosinase. Excessive productions of melanin causes long-lasting pigmentation disorders. And decolorization of melanin is an alternative method to treat skin pigmentation problem. So that's why we have studied the effect of free LIP, which is basically a lignin peroxidase. It's an enzyme and its hybrid complex with manganese, ferrite, and graphene oxide composites on melanin decolorization. First of all, in our experimental section, we have synthesized manganese ferrite by Sol-Gel autocombustion method. Graphene oxide was synthesized by improved Hammer method, and manganese ferrite was functionalized with graphene oxide by ultrasonication method. First of all, we take the X-ray diffractograms to confirm the purity and the crystalline phase of the synthesized samples. After confirmation of desired phase formation of graphene oxide functionalized magnetic nanoparticles, we simply immobilized that LIP on these nanoparticles. There's a hybrid LIP hybrid complex exhibited an immobilization yield of 96% at a LIP concentration of 0.8 to 1 mg per ml. This immobilization of LIP on nanoparticles was further confirmed by FTIR spectroscopy, and its magnetic study was done. Its magnetic study revealed the short ferromagnetic behavior of graphene oxide functionalized magnetic nanoparticles and LIP-based hybrid complex. The antibacterial activity and minimum inhibitory concentration of nanoparticles against pantoagglomerans pathogen have been studied. The nanoparticles showed an antibacterial action against the pathogen with an inhibitory zone of 7 mm and MIC value of 170 microgram per 100 microliter. These nanoparticles also degraded DPPH by 88% at a concentration of 180 microgram per ml. Decolorization conditions, including inducer concentration, incubation time, temperature, pH, melanin concentration, and buffer molarity for LIP-loaded hybrid complex and free LIP were investigated to optimize the best reaction conditions. We can see that from the graph, the melanin decolorization efficiency of LIP-based hybrid complex was almost twice time higher than that of free LIP under all reaction conditions. Next, the cumulative effect of many variables at the same time was studied using a statistical model based on RSM, which is a response surface methodology model. This chart shows the positive variables in orange bar and negative variables in blue bars. The positive variables, temperature, inducer concentration, and melanin concentration for LIP hybrid complex was carried forward for central composite design model. And we plotted these 3D graphs. These graphs generated from CCD model were dome-shaped and demonstrated the cumulative influence of positive variables. The model competence was determined by comparing the projected and actual values. The model competence was determined by comparing the projected and actual values in a fitted line plot. In current investigation, the anticipated and actual values were very close, which shows the competence of this model. The highest experimental activity obtained was 47%, and the anticipated value was 46%. e-SMYIM study showed the distorted order of surface of treated melanin granules, indicating the degradations of melanin. To sum up in short, I would like to say that this LIP hybrid complex improved melanin decolorization efficiency and might open a new route for the treatment of hyperpigmentation disorder. Thank you.
Thank you, Kiran. The next presentation is by Mithun. Mithun Mansudan.
Sir, can you hear me and see
Yes,
my
yes.
screen?
Yeah, I can hear you.
Sir, can you see my screen?
Yes, please go ahead.
Good evening, one and all. So today I will be presenting a talk on like scaling growing instability in plasticized polymer thin films. So initially I'll go through what is the motivation for this work, and then I'll just briefly describe the technique which I used, and then I'll go into the results. So polymer thin films are very interesting systems to work on because they show very interesting properties. So for example, I'll just take my pointer. Yeah, for example, I have given this figure here, which shows the decrease in glass transition temperature with film decrease in glass transition temperature with reducing thickness. So here the similar variation in properties were described earlier also by my professor when he gave the talk, which is regarding viscosity and elastic modulus. So these can be attributed to the increased mobility of the chains. Now, when we think in the bulk system, if you think about plasticization concept, so in the bulk system, when we add free small molecular diluent as plasticizer, it increases the mobility of the chains. And now when we put these both concepts into the thin polymer films, there have been some research that has conducted, and they have shown like the addition of plasticizer, exactly 4% of DOP, that completely removed the confinement effect, and it behaved exactly like neat polystyrene. So in other case, the effective viscosity of the film, that was unchanged, like after 1 million Dalton molecular weight. So now I want the research work which we did was like we selected a thickness near 90 nanometer, and then we added the DOP, 4% of DOP into it, and then the molecular weight was near 1 million Dalton, so there is no difference in effective viscosity. And then we wanted to see how it changes the dynamics of de-wetting. So de-wetting is a technique which I used to study, and just a brief introduction, like already Shiva sir and Mithun sir has elaborately mentioned about de-wetting. So I'll just say, like, de-wetting is just you're following the instability, that is a hole which is formed on the film at above glass transition temperature for a specific duration of time, and from the growth of the hole we get chain level dynamic information. So for example, in this paper here, we have got the paper effect. There are two slopes. The first slope, which is which is having a -1 slope, that is the region where the preparation induced residual molecular recoiling stress, or commonly called as residual stress, that is getting relaxed. And at a particular point which they have named tau1, that is the stress relaxation, residual stress relaxation time. And after that, it shows a characteristic viscoelastic de-wetting, which is having a slope of -1/2. So similarly, if we look at the rim collected, which is collected around the hole, we can see like the width of the rim increases to a maximum value, which is also near tau1. So this says like this width of the rim and change of slope can be taken as indication of how molecular recoiling stress is getting relaxed. Now, on coming to our result, what we did was, like, initially we added 4% DOP and did de-wetting experiment, and we could find that there is a drastic increase in initial slope, and also the relaxation that for a neat polystyrene, where the residual relaxation happens at around 1000 seconds, that got advanced to 150, around 150 seconds on addition of 4%. So, but then we increased the concentration by 8%, and then for 20% also, we could get that we could see that the slope of velocity decay is increasing further and further, and it is like very high values, which has not been seen in de-wetting before. So when we compare the velocity with the rim width of the rim that we obtained, the width of the rim is also getting a maximum value near to the point where there is a slope change happening. And but for the neat polystyrene, it is not happening like that, and it is near to 1000 seconds. So we wanted to further see what is happening really. So is it because of increase in the increase in the modulus, like due to antiplasticization effect, or etc. So now we went to the AFM profile. So AFM profile of a 4% and 8% DOP, we can see that there is increase in height of the rim. So increase in height of the rim can be considered as the strain on the film. So when we see that there is an increase in strain on the film, that could be due to increase in driving force, or due to increase in decrease in modulus of the film. So we needed to find like what is the driving force that could, if there any variation in the driving force. So we did an experiment on one single percentage, that is 8% DOP, and then we varied the spin speed from 2000 RPM to 10,000 RPM. And we could see that all the curves fitted to the same slope of -1. And after that characteristic relaxation time around at 150 seconds, the slope changed to characteristic viscoelastic de-wetting regime. So now then we wanted to see, like, in low molecular weight also, is it showing like this? So in normal core scenario, if we add a plasticizer to already low molecular weight polymer, it should show a viscous kind of flow, or it should not increase any stress in the field. So, but when we did that, we could get a scaling of around -0.7. So this could be like, if we see the concept of antiplasticization. So in antiplasticization, the molecules for low molecular weight molecules can get antiplasticized by adding plasticizers. But we are not sure like if it is due to antiplasticization effect or due to interfacial friction getting modified. So in summary, we could decouple the increased decay in velocity from residual stress effect. So then increased steepness of the rim width profile could point towards like the something happening near the interface where the friction is getting modified. And low molecular weight data could point us towards like either antiplasticization effect or the effect of interfacial friction. Thank you, sir.
Okay, thank you, Mithun. Now the session is open for questions. You can ask questions to Kiran and Mithun. Go.
I have a question for Kiran, actually.
Please.
Kiran, are you around? So I saw you showed your graphene oxide, and it seems like you don't. I mean, in some cases you showed a 001 peak or 100 peak, and that was missing. So basically, the interplanar, the peak which defines the interparticle distances, that's
Yes.
missing. So are you saying
Yes,
that
it's missing in composite because these nanoparticles are growing in between the layers of these graphene oxides, and it just is interlayer stacking. So in final composite pattern, that peaks disappear.
so? I mean, are they completely separated or like completely
It's not
delaminated or?
completely separated. It's just that the layers are
So you will
destructing.
see it in,
Layers are
will you still see it in, let's say, a small angle regime or no?
yes, sir. Sorry, sir.
Will you still see that kind of distance in a small angle regime? You're showing a XRD pattern here, right? Which is
There is just
you're very
only XRD pattern.
okay. Fine. That's...
Okay, next question from Sivasundar.
Yeah, this is for Mithun.
Yes, sir. Please.
Yeah, Mithun, the slide where you're showing this different preparation rate and all the velocities are overlapping one on each other,
Yeah.
deviating velocities, and that was quite surprising. So did you change? So you made sure that the film thicknesses are same or not?
Yes, sir. I made sure the film thicknesses are the same.
So you appropriately,
it is
ramped
not
up the
coinciding with each other. I was saying about the slope; they followed the same slope.
No, it looks like they're coinciding. If you can share the slide, it looks like it has more or less the same velocity.
Yeah, it has more or less the same velocity.
So that indicates that your plasticizers are already relaxing the stress.
Can you see the films?
Yes. No, I don't see the full screen, but I see the data that I'm speaking about.
Now, can you see?
Yes.
Yes.
If you can go to that specific, yeah, exactly. So here, if I see the initial velocities and so the film thickness is 90 nanometer.
Yes, sir.
And so you have a percentage of DOP. All of them are 8%.
Yes, sir. All of them are 8%.
Okay, so that's what. Maybe it's just that it's already quite high in terms of the plastic content, and your stresses are possibly not surviving at that temperature already.
Sir, but okay, sir. But then the entire stress is finally getting relaxed at a single point, no?
That is not. I mean, this -1 is not always for stress. It can also be for the nonlinear friction at the substrate.
Yeah, obviously. So
right. So you don't yet know what is causing your your -1-ish slope. Okay.
Sir, I didn't get you.
So you see -1 slope, and there are two ways of interpreting it.
Yeah.
One is presence of stresses, and another is presence of nonlinear friction at the substrate.
Yes, sir. I know that.
Right.
Yes,
so
sir.
it is not clear what you have, but the fact that you are 2 to 10 RPM is almost one on each other, and then you don't see any velocities. Did you actually caught all these holes at, what is the delay time or what's the incubation time of these holes?
Incubation time of these holes?
Like how long you have to wait before this holes popped up?
So it popped up instantaneously, like after, if I'm following it from initial 0 seconds. So initially, what?
He is asking you, let's say here in this plot, your x-axis, the 0 time is basically the time when you see the hole. He's asking how much time you took to see the hole. Let's say
So if
when
you are asking like with varying velocity, did you find any difference in time that is?
No, I'm just asking if all of these holes are captured right at the initial time, so that your residual stresses are represented properly.
Sir, holes are getting captured at maximum possible, like minimum possible time, because at 8% DOP, the hole growth is very high. So within 1 second itself, the radius of the hole increases very much. So from the moment that I capture, so that is why you probably saw that difference in radius and the velocity. You said velocity is at 0.1, the radius is at 1 micron. That is why that difference happened. So velocity, my minimum time for capturing is just 1 second. So by the time I click it, the hole has already reached a thing.
So then it just says that your film is already fluid enough.
No, sir. Sir, another thing is, sir, initially when we are considering about relaxation of stress, so the until tau naught, like initially when the hole is opening, there will be a viscous regime. So at that portion, we are not expecting any residual stress relaxation, right, sir?
That tau naught you will not be able to see for the molecular weights that you are working with. So that
Sir,
is not accessible for you.
Sir, but when we are adding DOP, we are completely like it could also be varying the viscosity of the system. That could reduce the viscosity of the system. So it is possible, it could be possible that we are also seeing that phenomenon where there is an increased tau naught, and after that relaxation is happening.
Highly unlikely.
Okay, sir.
But we can discuss this more, but that's highly unlikely.
Okay, sir. So I just had one question, sir. So
yes,
initially, if we are we are just following from the initial zero hole radius, so we are already capturing that effect of viscous area. So I am already getting a plateau in the holes which I have captured, a plateau of velocity. Okay, so that region we can consider as a tau naught region, right, sir? Because there is no decay in velocity. As per residual stress theory, there should be decay in velocity when we do de-wetting.
Since you are saying the VM part,
yeah, I am talking about the VM
no,
part.
I understand the first 3 points. For example, if I look at your velocity here in the bottom panel, the first 3 points are actually rather increasing, and then it remains constant. So because you see this increasing, you want to compare your data with tau naught. Is that
no, sir? You are talking about the low molecular weight sample. This one. No, I am not talking about that, sir. This is a high molecular. This is a low molecular weight. It is completely different behavior. I'm talking about the high molecular weight. So this will be the graph.
Okay, you see this constant, no? So what is?
Sir, see, I am seeing this constant, sir. So and see the velocity is just over 1.1 microns. So if residual stress is happening from here, it should not give me a constant velocity. Anyway, driving force is decreasing.
Constant velocity. So that's what I'm saying. It's not only one factor. There are multiple factors which decides the scaling laws that you are seeing. Okay.
Sorry to disturb you.
Sure.
Yeah. So we'll move to the next session. If there are no other short questions,
we can catch up later.
Yeah, sure.
Okay, sir. Thank you, sir.
Ravi, you are muted.
Oops, sorry. Next talk is by Mano Balan. Could you please share your screen? After Mano Balan, Muhammad Rizwan is the next one. Please get ready. Manobal, can you open the PPT? We can't hear you also. Sunita, can we just go ahead with the next one and then come back to the Mano later?
I think that sounds good.
Yeah. Okay, so I request Muhammad Rizwan.
Yes, sir.
Yeah.
Can you hear me?
Yeah, please.
Can you see your whole screen?
Not yet.
Full screen?
We can't see your presentation yet. Yeah, it is coming. Yes. Yeah, you can go to the full screen mode. Yes. Please go ahead.
Good evening. I am Muhammad Rizwan, research scholar from BAT, working in the polymer high voltage insulator under the guidance of Dr. Muhammad Rian Chandan. Today I am going to discuss about the influence of micro hybrid filler on dielectric and surface hydrophobicity property of EPDM composites, ethylene propylene diene monomer composites. Here, as we know that the conventionally ceramic material are used as the high voltage outdoor insulator in the transmission line, in power transmission line. But the advantage of using our polymeric insulator over the ceramic insulator is it reduces the cost, light in weight, and easy for manufacturing, which reduces the tracking resistance. These are the some of the advantages of using polymeric insulator here. In alternate of poly, in among the ceramic insulator, EPDM silicone rubber is mostly used by industries to manufacturing the polymeric insulator, and our focus is to develop the EPDM based insulator. Few of work is going on to develop the EPDM based insulator, polymeric insulator. And then the property of polymer, the dielectric property of polymer is improved by adding the filler. Filler play a major role to improve the properties of the composites. Here, our work is focused on purely EPDM, ethylene propylene diene monomer based polymer to develop, which fulfill the industrial standard here. Based on the literature survey, we have based on literature survey and previous work we conducted, based on that, we have chosen the magnesium hydroxide as the microfiller here, micro reinforcer, and titanium oxide and boron nitrate as the nano reinforcer. The EPDM composites of various composition have been mixed using the open two-roll mill and then vulcanized by using the hydraulic compression molding at 170 degrees Celsius for 10 minutes. Here, the peroxide system of cure. Peroxide system is used, dicamyl peroxide is used, and coagent 1.5 PHR is used here. Here, in table, we can see the composition of micro composites as well as the hybrid composites here. In hybrid composite, we blend the nano filler as well as the micro filler here. And the dielectric breakdown strength is one of the major property to evaluate the performance of outdoor insulator, as well as the wettability studies, wettability static measuring the hydrophobicity, and the surface morphology of composites have been captured by using SIM imaging. Here, in this result and discussion section, we have clearly observed that the micro composites, the inclusion of microfiller in EPDM matrix shows the enhancement in dielectric strength. 30 PHR filler shows the maximum enhancement here among the microfiller, which is nearly 17.4. And in case of hybrid filler composites, hybrid filler, the 3 pHr of boron nitrate and microfiller of 27 pHr has shown the maximum dielectric strength value of nearly 21.2, which is 19.3% enhancement with the microfiller, 30 pHr microfiller. Among the best microfill composites, from comparing with 3 pHr composites, shows the maximum value, maximum dielectric enhancement of 19.4%, and nearly the TiO2 does not have much enhancement. It has enhancement compared with the microfiller, but not much as the boron nitrate here. And interestingly, if we compare the hydrophobicity property of the composites, we observe that in microcomposites, the EPDM gum without filler compound is hydrophilic in nature, which shows hydrophilic in nature. And inclusion of microfiller increases the contact angle up to 30 pHr, further increasing that it will reduce. And in case of same trend is seen in the hybrid composites also. But here the noteworthy thing is TiO2 composite shows maximum contact angle here. This will be explained. The reason will be explained in upcoming slide. Mechanism behind this. Here we have seen the same image, same morphology image of the micro as well as the hybrid composite. We have seen that 30 pHr micro composite shows the even dispersion of filler and increase the filler content, which show the rough surface, rough morphology on this. And if we compare the same imaging of nano composites, 1 pHr nano filler composite shows the up to 3 pHr, we have seen the densely particle. Above 5 pHr, we have seen the formation of agglomerates here. These are the same images of micro as well as the hybrid composites. And in this mechanism, this is the interesting mechanism which we have predicted, argue with this study. Here for micro composites, up to 30 pHr composite, we say up to 30 pHr composite, the particle concentration is lesser than the percolation concentration. The filler is evenly dispersed in the EPDM matrix. Here, MgOH filler is evenly dispersed in the EPDM matrix. When the filler concentration increases above the percolation concentration, particle concentration increases above the percolation concentration, there we have seen the formation of agglomerates and voids in between the filler, which is the reason of filler-filler interaction take place. But in case of micro hybrid filler composites, we have seen the same trend here. Here, up to 3 pHr of adding nano filler in EPDM matrix, which form the continuous path, which has homogeneous dispersion in filler matrix here, which form continuous channel here, continuous channel to heat flow here. And in case of 5 pHr nano filler, we have seen the filler-filler interaction take place, and as well as the nano filler interaction take place, and microfiller nanofiller interaction take place. And the reason why the dielectric strength value increases with the filler content increases, because here we seen in the microfiller case, there is the formation of filler-filler interaction. In dielectric strength, when the material is subjected to the electric field, high electric field, the breakdown will be occur. It will be the electrical energy is dissipate in the form of heat. While filler concentration increases, here we form the pockets of filler pocket, which lead to store the energy and resulting the damage of insulator here. This is for microfiller. In the case of nanofiller, if we have 3 pHr filler having the very less distance between the filler, which gives a continuous heat flow, continuous channel to heat flow here, which dissipate the maximum amount of heat, which lead to withstand the maximum voltage. But in case of nanofiller, the same phenomena in microfiller, this will be happen here. Like for nanofiller interaction resulting to trap the heat energy inside the polymer matrix, which lead to failure of insulator. In case of hydrophobicity, we have seen EPDM matrix is having a
can you please wind up?
Yeah, ma'am. Only a few minutes, 1 minute, I will be wind up. In EPDM matrix, the hydrophobicity is having which porous nature from the same imaging. It will, because of Benzil equation, it has porous surface is act as hydrophilic. Inclusion of filler, which increase the hydrophobicity contact angle value. If the filler concentration increase the percolation concentration, filler filter interaction increases the surface energy. And finally, this is the reason at higher filler loading, the hydrophobicity will be affected. And then I conclude this speech by comparing with the commercial standard value. We have seen that the commercial Indian railway standard value of dielectric range is 17.5. By inclusion of, we have seen nearly the 30 PHR microcomposites have nearly close value to commercial standard, but all hybrid composites are passed through this limit. And amazingly, the 27 MgOH and 3 boron netted composites show 21.06 here because of boron netted is higher thermal conductivity and Ta. I will end this speech here. If you have any questions, kindly you can. Thank you.
Okay. Thank you, Mohammed. Manobal, can you please try again?
Sir, am I audible?
Yes, yes. Please share your screen.
Sir, is it visible, sir?
Not yet. We can't see. Yeah, it is coming now.
Is it visible, sir, now?
Yes, yes. Please go to the full screen mode. Yes.
Can I start, sir?
Yes.
Good evening to all. I am Manabalan, research scholar under the guidance of Dr. T.P. Somola from Vellore Institute of Technology. Here I am going to present the topic enhancement of EMI shield effectiveness using nickel ferrite in graphene epoxy composite. First of all, the EMI is a disturbance caused by an electromagnetic field to operating electronic devices. So to shield this EMI, researchers are used conductive and magnetic materials like graphene, CNT, nickel ferrite, cobalt ferrite, like that. So here I used graphene and nickel ferrite. So already researchers are reported these compositions, but with more concentration they are used, like 15%. So here I used very less amount of concentration, like nickel ferrite is 5.8% and graphene is 0.88% to enhance the EMI shield effectiveness property. So my these composites are less weight, low cost, and simple to make a film. So this is the schematic diagram of our composite. So this is the XRD of our composite. So this is the epoxy, and then graphene epoxy, nickel ferrite, and graphene epoxy with nickel ferrite. So these indication of planes are confirmed by that JCPDS data. So this is the same image. This is the pristine image. A is the pristine image, pristine epoxy, and B is the graphene. So you can clearly see the graphene are very well dispersed in this B image. And then C is graphene epoxy with nickel ferrite. So here you can see the nickel ferrite also we will confirm by using this image. So then next, conductivity. So when I added graphene, so our conductivity is increased. Then I added the nickel ferrite, it decreased. So when graphene alone added, that conductivity is increased. So here the Young's modulus of the pristine epoxy is the maximum. So here we can clearly see when I added the nickel ferrite, we get a maximum EMI shield effectiveness compared to other composites. So I took the expand for this shield effectiveness. So graphene epoxy maximum seal effectiveness in minus 14.5 decibel at 11.9 gigahertz. So finally, I conclude this work. We studied composites of graphene epoxy and graphene epoxy with nickel ferrite. So here I conclude, when I added nickel ferrite, I got good results of AMI shield effectiveness because of its conductivity as well as magnetic property. So the nickel ferrite promisingly helps to enhance the shield effectiveness. Thank you, sir.
Thank you, Manu. Now the session is open for questions. One can raise your hand or you can ask directly. Unmute yourself and ask questions. Okay, Mano, I have a question for you. Just so can you go to the conductivity data? Slide number 4. Yes. So here you are saying your graphene, I mean, when you add graphene oxide, your conductivity is higher.
Yes, sir.
But
At this
you see
frequency.
this epoxy is higher than the other two, right?
Yes, sir.
How can you say graphene is more conductive in this when you add graphene?
So graphene is a very good conductivity material. So here you can clearly see that percolation threshold also increasing, and this particular frequency is the maximum for graphene epoxy.
Okay, it is a frequency dependent conductivity. Okay, yeah. So if there are any other questions, please unmute yourself.
I have a small question.
Yeah, please.
Mano, what is your idea about the percolation length in this system?
Your question to so Mano or Mohammed?
This conductivity one, the current one.
Okay, right.
Yes, sir. What's the question?
I mean, what is the percolation length you expect when you are mixing these graphene and epoxy? Means the length scale where you can get a, let's say, interconnected network where you can expect that is that should be responsible for good conductivity, na? That we call percolation length.
Yes.
Do you have any idea of the length scale? Is there any agglomeration or anything else?
Yes, sir. Graphene also got gets agglomerate. I don't have an idea about the length scales.
Okay.
Okay, so there are no other questions. Let me thank Manu and Mohammed. So let's move to the next session. The first talk is by Andri Sharma.
Can I share my screen?
Yeah, please share your screen.
Okay, wait. Is it?
Yes, sir. Yeah, you can go to full screen.
Is it visible?
Can see, but it's not in the full screen mode yet.
Now?
No.
Can you see it now?
Not yet.
My screen is visible or not? Is it visible?
Your screen is visible, but it's not in the full screen mode, or we can't see your presentation.
You should select normal in that, and then you can go back to those options that you are checking.
Okay. Normal.
Yeah, select normal. Then one of the options towards the right, if you can go to your menu. Not there, on the top.
On the top right. This one.
No, no. Even higher, like you open some stuff, right? Yeah. Start from current slide. That one. Yeah. Next one. Yeah.
Current slide. Can you see it now?
No, it's not gone, no?
Not yet. Okay, so you can.
Can I present it like that? Because I think it's not showing here. I don't know.
Like on your right side, there is a icon which is like a play video towards your right on top. Go up.
This one?
No, towards your right.
The next side.
The next side.
Right corner.
Yeah, just there's a pause button, there's a play button. Go there and see if it plays. No, left to that.
This one.
Next, and then next. This one.
Yeah. Now can you see?
It doesn't.
Okay, no problem. So I
No
think
problem.
there is some problem. So you can at least minimize the slides. Yeah, this one. Yeah, you can start presenting.
Okay. Good afternoon, everyone. So sorry for the inconvenience, but can you hear me now?
Yes, we can hear you.
Okay. So my presentation will be based on the work which I'm doing in my PhD, and it is purely computation, and it is motivated by the experimental work people have done in the past to understand the function of biological cells. So the cells is actually inside a membrane along with different DNAs and RNAs and different macromolecules. So it is seen that whenever not all, if few of the DNA or RNA passes from the membrane through the pore attached to the membrane, the cell functions. So this is very important, that the transportation of the micromolecules is a vital role to understand the cell function, and motivated by that I am continuing my research. So as you can see, the snapshots are from my simulation result, and I'm using Langevin equation to solve the problem. And to take into account the pore effect, since my pore is conical, the force is actually not constant. It is rather dependent on the alpha, and d is actually the width of the pore. The more along the more wider the pore is, the less will be the effect of the pore. So what? So, sir, my screen is visible or not?
Your screen is visible, but it's not moving. It's not moving to the next slide.
Oh, it is showing here. Why it's not visible?
Danny?
You can manually go to the second slide and
You should just come out of slideshow and simply just move slide by slide. And right, we can see the second slide now. You can maybe talk.
Yeah. So what I have done, since I'm trying to understand what happens inside the conical pore. So my pore is so what I have done, I have changed the alpha angle from 0 to 20 degrees, and I've changed the magnitude of the external force from 0.9 to 0.1 to 0.9, and I've seen that as I go to 0.9 force, the translocation time versus alpha plot becomes straightly increasing function of alpha. While for lesser force, we can see that for 0.1, 0.2 or 0.4, it is a beautiful non-monotonic pattern of alpha rather than a increasing function of alpha. So the minima is 1.5 degree and the maxima is at 3.5 degree. And the minima and maxima itself carries a lot of information about the pore, the confinement of the polymer inside the pore. So this process is forward translocation. This is just a terminology which I am using for reference. From narrow to wider, I am calling it forward translocation. And so and the same thing I have.
You have to click on normal there.
You can reopen your slide. Please close your presentation and restart again. I think it may work.
Can you see it now?
Not yet. Did you open?
Yeah, it is open.
Okay.
You'll have to share your screen. You stop sharing the screen. While you try to do so, please share your entire screen. Don't share only your PPT.
Yeah, we can see now.
Yeah, now can you see the screen?
We can see, but slides are not moving still. I remember you are in slide number 3, right?
We can see a
Now
slide.
it's working. Yeah, now it's working.
Yeah, please go ahead.
Sorry for the inconvenience. So the first slide was just the explanation of my computational setup and the motivation, and the second slide I have just told you the main experiment what I have done to the variation of the translocation, total translocation time with alpha, and I came to the conclusion that it is better to work in the low force regime to get all the information about the pore. And at the lower forces, like for example 0.1 degree, there is minima is at 1.5 and the maxima is at 3.5 degree. and this is forward translocation, and the same I have repeated for the reverse translocation, where the transport was from the wider end to the narrower end. And I found, and as you can see in figure 3.8, the blue one is for reverse translocation and the red one is for forward translocation, and the disparity is very huge. Like the translocation time for the region of 0.1 to 0.29 alpha is very high, and this result is in agreement with a paper which was published in Nature in 2018 by Nicholas L. W. Bell. So I try to study the same for high rigid polymer 2 and 4, but like there is a disparity. There is a disparity between the translocation time. The blue one is still higher in 2 and 4, but the non-monotonicity is lost, is completely lost. And so I come to the conclusion that to study the, if I want to purely study the effect of the pore in both directions, forward and reverse, flexible polymer is the best choice to do it. So to understand what happens within the pore and what happens during the process, one can and study the waiting time distribution. And waiting time is basically defined as the time spent by each monomer inside the pore while transporting. So as you can see in figure 4.A and 4.B, 4.A is for forward translocation and B is for reverse translocation. So the red one is for alpha equals to 0 degree, like non-conical pore, just extended pore, which is a 4-step process. But as I increase my alpha, the important part is to see the exit behavior. Like when the polymer is starts exiting it, the slope decreases with higher alphas, but in reverse case it increases. So that in the forward translocation, the multi-beat transfer is seen through this decreasing slope, while in reverse translocation, where the entry can be multiple beat, but the exit is beat by single file translocation, it smoothly increases with at the exit point while exiting the pore. So so people have done this experiment through nanopore, single pore experiment, and there is a perfectly beautiful and well matched theory, which is transfer tension propagation theory. So I have tried to map my simulation results to that single pore experiment. So as you can see, my in my simulation, the red one is for extended pore, alpha equals to 0, and there is 4-step process. There is not directly propagation and retraction part. So what I have done, I slowly increase the force to see how the behavior changes with increasing force. So I have seen that when I come to the regime of 1.5 greater than 1.5 strength of the force, external force, so this black one and the magenta one, we can see that there is a tension propagating and retraction part is there. It means that the whole extended pore can be mapped to a single pore, but the information about the extension is still there, which is carried in the first and the last exiting pore. So I come to the conclusion that one can easily say that extended pore acts as a single pore after the pore is filled and before the exit of the pore. So in between this picture, extended is equivalent to the single pore experiment. So what I conclude from my project is that the best choice of to study the disparity between forward and reverse, which I already told, that it is flexible polymer, and the angle at which it shows higher disparity is 3.5 degree. So at 3.5 degree, very interesting thing happens, like because since the extension, the wider extension allows multiple folding in multiple fold during the entrance in case of reverse translocation, and during the case of forward translocation, and the coiling effect in case of reverse translocation. So yeah, so this is what I got it, and the whole simulation process was performed through a software called LAMPS. Thank you.
Okay, thank you, Andres. The last talk is by Sipra Mohapatra.
Yes, sir. Thank you, sir.
Please share your presentation.
Yeah. Yes, I'm sharing. Is it visible?
Yes, please go ahead.
So, yeah. Good evening, everyone. I'm Shipra Mahapatra from IIT Jodhpur. I would like to thank the organizer for giving me a chance to present my talk here, present my work here. So today I will discuss about today I will discuss about the molecular mechanism of ion transport in polymer based battery electrolytes and the effect of succinonitrile on it. So as we know that lithium-ion batteries currently there has been an increasing demand for safer and high energy storage devices, and lithium-ion battery is also one of them. So in batteries, electrolyte act as a medium for the transportation of ion in between the electrodes, that is cathode and anode. When we are talking about solid polymer electrolytes, so polymers are used in solid polymer electrolytes for the transportation of ion. And in this animation also you can see how the ion hooping happens in polymer electrolytes. We have used PEO, polyethylene oxide, as polymer in our system, and lithium TFSI salt, and we have also used succinonitrile, which may act as a plasticizer for our system. So plasticizers are commonly used to reduce the crystallinity of polymer matrix, and which can increase the flexibility of polymer. So after adding this succinonitrile, can succinonitrile enhance the diffusivity of ion in polymer electrolyte? And the main goal for me is to know what are the underlying mechanism of the diffusivity of ions. So this is the simulation details. To know the effect of temperature and effect of loading of succinonitrile, we have performed all molecular dynamic simulation at different temperature, and after by loading different weight percent of succinonitrile, we have used OPLS forceful parameters to perform this simulation, and we have tabulated the equilibration protocol that we have follow for our simulation. And this is a visual impression of equilibrated system after 300 nanosecond of succinonitrile loaded PEO LiTFSI electrolyte. So to investigate the diffusivity of ion, we have calculated the mean square displacement and diffusion coefficient. So maybe yeah. So in this plot, you can see that the mean square displacement we have compared the mean square displacement with 0 weight percent and 2 weight percent of succinonitrile for both lithium and TFSI, and both are increasing after adding succinonitrile, and the diffusion coefficient is also increasing with weight percent. And here is a plot for different temperature. We have increased the temperature and also got the diffusion coefficient for lithium and TFSI both are increasing with temperature as well as the weight percent of succinonitrile. Now we got an answer that actually succinonitrile is increasing the diffusion of ions, but our goal is to know what are the mechanism behind the diffusion of ions. So there must be some relaxation phenomena which are included in the diffusion of ions. So according to Stokes-Einstein relation, so diffusion coefficient is inversely proportional to viscosity, which is also equivalent to the relaxation time. So can any relaxation phenomena explain diffusion? So for that, we have calculated ion pair autocorrelation function and dihedral autocorrelation function by using this formula. And what we observed is the ion pair autocorrelation function and the dihedral autocorrelation function are decreasing with increase in temperature, and the relation of what we got for diffusion coefficient with time, relaxation time, is conclusively explaining the diffusion of ions. So these are my conclusions. So classical MD simulation were performed to study the transport mechanism of ion with SN loaded system, and succinonitrile can be used for the future lithium-ion battery applications. And the cation anion interaction and the polymer segmental changes influence the diffusivity of ions after adding the succinonitrile and PEO based polymer electrolyte. So therefore, ion pair relaxation and polymer dynamics conclusively explain the diffusion of ion. So I'd like to thank my supervisor, Dr. Santosh Magurampalli, and my colleague, Mr. Shubham Sharma, and IIT Jodhpur for the DGX facility. Thank you. I'm open for questions now.
Okay, thank you, Sipra. Now the session is open for questions.
Yeah.
Can I go ahead, Ravi?
Yes, please.
Yes. Shipra, thanks for showing this nice set of data. So this D which you got with time, is this, I mean, it doesn't look like a, I mean, it's not a single monotonic region. I mean, it sometimes looks like it's not like a, I mean, is this subdiffusive or super diffusive, or how do you got this? I mean, go back to the slide before.
Yeah, this one.
Yeah, this one with temperature. Yeah.
Yeah, sir, we have checked by fitting the equation that we have got for MSD, and we got it in diffusive region actually. For TFSI, of course, and for lithium also, it's means exponent is nearly equal to 1.
Okay, exponent is nearly equal to 1. Okay, then diffusive region.
Yes.
But the shape was a little bit confusing. I don't know why. But anyway, this D and 1 by tau, I mean, I understand that is something we consider, but that sometime, quite a lot of time, they don't couple. So the D and tau could be different. So in the next slide, how do you got this? How are you concluding that segmental relaxation is, or segmental level relaxation in polymer chain is also responsible for this behavior?
Yeah, sir, sir, we know that from literature that EO section of the PEO polymer is interacting with lithium ion. It has a high donor for lithium ion. So then we have considered that COCC dihedral for calculating the dihedral autocorrelation function, and we have calculated the correlation between polymer dynamics, the interaction between the polymer and the lithium ion by using this formula.
Yeah, I mean, at the monomer level, there would be, of course, some interaction because it's like ethylene oxide and then lithium plus. Now, I was thinking whether have you been increase the length scale to few segments or even a small chain kind of thing?
Yeah, we have calculated for the whole chain. We have considered many chains, and we have also calculated for every chains.
Okay. Okay, fine. Yeah.
More questions? Okay, fine. So if there are no more, let us talk.
Okay, sure.
Thank all the speakers for all the mini talks.
Okay, thank you, sir.
That brings to the end of this mini talk session. So over to you, Sunita.
Thanks, Ravi, for chairing the session, and thanks all the speaker for this session. Since we are running little late, maybe we can skip the break. And I will also request, if possible, the participants can turn on the video, that we can take a screenshot for the virtual photo shoot or picture of the session. And then we'll start the next session for the keynote speaker. Okay, smile, please.
So many are active at the end of the day still.
I'll just take one more and then we can.
Maybe Sunita, just a minute. The people turning on.
Still okay. Can go ahead, I guess.
Yeah.
Okay. Okay, thank you everyone. So the next session, Dr. Vasa from IIT Madras will chair. Vasa?
Yeah. Yeah. So yeah, I think that this Professor Kakkar was supposed to be giving an in-person. I mean, not in person, but yeah, he was supposed to be. This was supposed to be a live lecture, but for some reason, I think he's not available. So therefore, he was kind enough to agree to give a recorded video for us. So I think what we're going to do is to play a recorded video, right, Sunita? That's the schedule.
Yes.
Yeah, right. So yeah, so before we play the video, I think all of you may know Professor Kakkar already. At least the people who work in Chemi for sure knows Kakkar, because he's one of the very well-known people in the field he works on multiple areas. So just to a brief introduction. So he finished his PhD, bachelor's from IIT Delhi in 1981, and he holds a PhD from University of Amherst in the US. And so he's been at the Department of Chemical Engineering, IIT Bombay for a long time, and he was also the director of IIT Bombay for a couple of years as well, couple of terms as well. And he works on a variety of different areas, fluid mechanics, granular material, and he's also recipient of many prestigious awards, including the Swarna Jayanti Fellowship as well as Bhatnagar, Shanti Bhatnagar Prize as well. So with that introductions, it would be nicer to have him in person, live, because we could probably learn a lot from him in terms of how to go about. I think and also he's also in a lot of funding, body. So therefore, I think it would be nicer to learn from him, both in terms of the academic learning as well as in terms of how does one approach a funding situation as well. So, but hopefully, we'll meet him at some point, and then he'll be able to enlighten us with all those things. So maybe with that, we could have Sunita. We can start the video, and then maybe I don't know if there's a way to interact with him. He's not available, right?
But he did agree that any questions if we have, we can send him an email, and he should be able to get back to us.
Sure. Maybe we can make note of some important questions, and maybe we could share it with him. Yeah.
So Danny, you are sharing the link.
Yes, I'll do that. Can you see it?
Yes, it's visible. Yeah.
I'll play it. If the audio is bad, let me know.
Sure.
Good evening. Today, I'm going to talk about
obstructing the view.
Securing and managing your research grant. I'd like to start with a thanks. Thank you for inviting me. And also, I'd like to apologize. I'm sorry I can't be with you live for this lecture because I'm out of town. However, if you have any questions at the end of this lecture, please contact me on my email, which is given here, and I'll be very happy to respond. So, though I work in areas related to soft matter. The organizers asked me to talk about securing and managing your research grant. And I guess I'm qualified because I've been in this system for a very long time. I have
There is no audio.
Yeah, Danny, we can't hear
Neither
Shankar
can-
anymore.
One second.
say a few
I
things
think this
about
problem.
what are some of them.
Stop suddenly.
And also I'll say a little bit about the outline of my keys which are giving out. The system.
Just give me a second. I think there's some problem. I'll just share this again.
Also, I'd like to happy your research grant. And I guess I'm qualified because I've been in this system for a very long time. I have
Danny, I think we can skip those few seconds because there was some glitch in the video during the recording.
This is going to be
okay.
The outline of my talk. I'll say a little bit about why everyone should try and seek funding, including those who may not need research equipment. I'll say a little bit about what are some of the funding sources that are available, and then what are some elements of a good proposal, and finally, how one should run a project. Of course, I can't go into every detail of each of these topics, so I'm going to just say a few things that came to mind. I should mention that I had given a similar talk in a workshop that was done in a department, which was done for actually PhD students and postdocs. And in that, my co-author of this presentation was Professor Jason Picardo. So, we worked together to develop some of these ideas and the presentation itself. And when I was asked to give this presentation the first time, I talked to Professor P.V. Balaji, who is the former Dean R&D, for his help. And he gave several inputs which are included in the presentation. And also Professor R. Raghunathan, who is from IIT Madras, Chemical Engineering. Professor Raghunathan served with me on the Program Advisory Committee, which is the committee that decides on giving grants for SERB in chemical engineering. Excuse me. And of course, when I was trying to collect material about sources of funding and all, the staff of IRCC helped me out. So I'd like to acknowledge their help as well. So let me start with the first topic. Why secure a research grant? Of course, if you're an experimentalist, then funding for major equipment helps build up facilities in your lab. And usually this is done over several grants because most grants will maybe give one major equipment. Again, if you're an experimentalist, you have quite large running expenses for the lab, and often the projects are very much essential to get the funding for consumables. It's nice to have some funds for local travel, so you can actually go and meet colleagues and so forth. And there is support for contingent expenses. Sometimes some equipment may break down, or you may need some money for conference registration, or you may want to pay some paid charges. And often, these expenses can come out of the project contingency grant. Very importantly, you can support a student or a project staff. But this is something that I found quite useful because when you write a project, it really helps you to define what your research direction is and what you're hoping to achieve. And I think, we always have this in our mind that I'm working towards this goal and so forth. But when you write it down, I think that is, much more. It becomes much more clear in your mind. And then, of course, once you write a grant, you're putting your ideas out in public, and you will get some peer feedback at an early stage. And I think this is also quite a useful sort of thing. You'll get some feedback, and you may find it useful, and then you can modify your grant, or you may modify your research directions as well based on this feedback. So now let me go to the second topic that I said I would discuss, and that is funding sources. There's several government agencies in India which support research, a very large number. There are some international agencies which you can apply to. Then, of course, industry sometimes will support research in areas of their interest. And many of the institutions are giving seed grants, and I think that's really a wonderful way to get started. And so I asked IRCC for information on which are some of the common funding agencies which support projects in IIT Bombay. And here is a list of some of these. What I'll do is I'll make this presentation available to Professor Sunita Srivastav. And so, some of this information might be useful for you. And so, you will get funding from so many different organizations, plus many of the ministries themselves have funding programs. And so, there are many opportunities to get funding, whether it's DRDO or DOE or CSIR, ISRO, and so forth. Even for a given funding agency, there are a large number of schemes and programs. And this is for SERB, which is perhaps our largest funding, along with DBT is one of the largest funding agencies. And you can see, there are so many different schemes, intensification of research in high priority areas, startup research grant, core research grant, and so forth. There's so many different, and each of these has their own aims and objectives. So you have to read what they're looking for. And then, of course, there are a number of awards and fellowships which also have funding for research, like JC Bose, Ramanujam, and so forth. And if you just go to their website and then you say, okay, I want to write a grant, you may come across something like this. And what it says is that, okay, there are these programs, but submission date closed since this date. So most of these research grants have a closing date. So there'll be a call and then there'll be a closing date. So you have to keep alert and keep track of when you can submit. Of course, this early career research grant is available all the time. So I think that is something that is nice. But for many of the others, and we often write this core research grant, which supports basic research, and it has certain closing dates. So currently, the proposals that were received in March are being processed, and then again, probably another few months they'll open it again. Now, there's so many options. So how do you choose which funding agency to go for? And here what I'd like to say is that each agency and scheme has certain priority areas. So you need to choose the agency and scheme based on what your research proposal is. So does it really fit in with what they are trying to support? So I think this is something that you have to see and search and see which has the best fit for your research. And then you need to understand how much your research is going to cost and estimate that budget. Because most of these agencies and schemes, they have some sort of notional maximum. It's not exact, but things go into a loop if it goes more than a certain amount. So I'm very familiar with the SERB, and for them, the core research grant, almost any grant, the limit is 80 lakhs. So if you want straight through processing, then your proposal should be less than 80 lakhs. If it goes beyond 80 lakhs, then it goes into another committee and it may take very much longer. So then in some funding agencies give much less, like CSR, maybe max is about 30 lakhs. So depending on what your research is, you need to choose your scheme and your agency appropriately. And then, of course, you have to be careful because every agency and every scheme has some specific format and you need to follow that. So that is also something that is quite important. Now, how should you write, when you're writing the proposal, what are some of the points that you should keep in mind? And again, these are some of them are my ideas, but I've also got ideas from Professor Balaji, from Professor Raghunathan, from other colleagues, and I've tried to put it all together, and just so that it just gives some ideas about what you should keep in mind when you start writing the proposal. And I think one very key thing is that what are the objectives? That should be very specific and clear, and you should define in the objectives the scope such that it can be met within the duration of the project. So if the project is 3 years, make sure that the work that you propose can be finished within that time and within the resources that are available to you. Of course, you must have a very good literature survey, because when it goes out for peer review, people, they judge how familiar you are with the proposed area by looking at what sort of perspective you give on the field. And you've got to be careful that the questions that you're proposing have not already been answered, and that the outcome of the project makes some new useful contribution. I think these are some of the things that people will look at. And then it's always useful not to keep the proposal too general. You must have some specifics so that people can judge whether the system is amenable for experimentation, the signal to noise ratio is good, the equipment is available, and so forth. And of course, many of us do simulations, and then you have to think about computers, whether you want to buy them or you're going to buy time. Things like this are something that one must think of. And this is also quite a useful tip, that have a plan B. Because very often, we have some ideas that we want to go in this direction, but for some reason it just doesn't work out. Or that you manage to do the experiments, but the outcomes are very different from what you imagined, or they're ambiguous. So then what are you going to do as a plan B? And I think that is something that is also something that you should keep in mind. And then, one of the things I've noticed that funding agencies seem to be very, very particular about is, this budgeting and finance and so forth. So you have to be careful about that. This is some more tips about proposal writing. And these are some things that might help. That have a good executive summary answering why the problem should be solved, why it has not already been solved, what is the key idea that will allow the proposer to solve the problem, and what will
Danny, again, I think the video, the
Yeah,
audio is lost. Yeah. Right.
yeah, it's a problem at his side only, I think.
Okay, no worries. Yeah.
Can I fast forward this a bit then?
Yeah, maybe we can do that little bit and then check.
then you'll be able to solve. Once those are addressed, then you'll be able to solve the problem. So this is the sort of background to the work. And then the method, how are the challenges going to be addressed? And really, this is where all the novelty is. That, what is it that you're going to do that is going to be different from what has already been done? And it always is useful if you've already gotten started and there is some prior work. So, you have maybe a proof of concept on the new method that you're proposing or the new approach that you're proposing. So there is some little bit of support for those ideas based on the work that's already going on. And of course, details of the methodology, what are the subtasks, how long will they take, and so forth. And how will one task support, or give information to the other, and so forth. So this is also very important for good proposal. And finally, what will be the impact? I think these things would be, these 6 points would be important to write a good proposal. Now, when you're actually doing the writing, there are some nitty-gritty things that might be useful to think about. And especially those who are new at writing proposals, these are some additional points that you might find useful. Many of the, in fact, every proposal format, they require you to say what are going to be the outcomes. So trained PhD manpower, papers in leading journals, books, software. The final outcome of the project. So, in most funding agencies, after the project is complete, you have to submit a project completion report. And then there is again a second review process. And the project is given some kind of grading, it's judged. And I think one of the things that reviewers often look at is how close do you come to the proposed objectives in the project. Of course, there is some flexibility to follow some unexpected results and so forth. But one cannot just put the major objective aside. Another thing is that, most of our funding that comes does not allow for international travel. That is, the current sort of rule. But there are many agencies in which you can write bilateral grants with collaborative grants with different colleagues with colleagues in different countries. And here are some of these mentioned. And all of these fund, if you think that you have a collaborator somewhere and you'd like to travel there, then approaching these kinds of agencies would be most suitable for you. Okay, so now we have written a proposal, submitted it. So what does the funding agency do? How is the proposal evaluated? Well, in many cases, there's often 2 stages of peer review. Now the funding agencies are getting vast numbers of proposals. So usually there is one peer review that is a sort of first cut and a simple thing that do you go forward or not. And then there is a second, those proposals that make the first cut, then go in for a detailed peer review by an expert. And these are generally anonymous, and each proposal generally has at least 3 peer reviews before a decision is taken. Some of the agencies will ask you to come and make a presentation also of the proposal to the program advisory committee. And based on these kinds of inputs, there are experts who are on these program advisory committees who make the decision. So as I've written, they're senior experts in the area. That means basically they've been through the system for a while. And when they're making their decisions, their main considerations are originality, feasibility, can you do this proposal at all? Utility, committee looks at. And these are the questions that are also asked of peers when they are writing their review. And I'm sure some of you may already be writing reviews of proposals, so you would also know that this is really what is asked for. You know, when I joined the system, I joined IIT Bombay in 1987. I joined IIT Kanpur in 86. But my first proposal was in 1987. In those days, you know, there was not much competition. So you wrote a proposal, you would get funded. But today, you know, there is really high competition. And, you know, I serve on the chemical engineering committee. And this, every 6 months we meet. I mean, we have a call for proposals every 6 months. And in the last 6 months, we received something like 434 proposals. And, you know, typically only about 10% or 15% of those proposals can be funded because of the budget limitations that the committee has. So really, this is something to keep in mind, that you do need to submit a good proposal and maybe submit to multiple agencies. Not the same proposal, but variants of the proposal, so that you can increase your chance of getting funded. Once you've written the proposal, or even while you're writing it, but before the project is sanctioned, you do need to look at specifications of any major equipment that you're going to purchase and get budgetary quotations so that you understand what is going to be the cost. In case you already have a student with you, it may be a good idea to get started on some aspects of the proposed research by making the work a part of the student's thesis. Again, this is whatever can be done with the existing facilities. So, you know, you might be able to do some amount of the prior preparatory work and so forth. In case you don't have a student, then start doing the work yourself. Again, whatever is possible. After the project is sanctioned, I think the first thing is to really start on purchase of large equipment, because this takes time everywhere. You know, there's so much paperwork and so forth. So it's good to get started quickly so that, you know, you have the equipment in place early on in the project, and then you can start producing results. Also, second priority would be to recruit a student or project staff. Now, you know, I've done both. I've hired project staff to work on the project, and I've often taken PhD students to work on projects. And I found that, you know, the second is often the one that produces the best outcomes. Because project staff, what I found was that most of them are there for a shorter period of time, and they, you know, are looking for their next position. So obviously they by the time they learn everything, they're almost ready to go. and they're just not there for long enough to start delivering real quality work. So whenever I have taken PhD student to work on the project and align the thesis objectives with the project objectives, I've had very nice outcomes. And one of the other things I often do is that if I know that I'm going to be writing a project or I've written a project, then I will often offer topics to students which are related to the project, so that there is a broad research effort towards the aim of the project. And then, so you have many different contributors, and eventually, you have a really nice amount of work that is done. And, you can more than achieve the objectives that you have proposed in the project. Another very important thing is to keep track of finances. They ask for annual accounts, utilization certificates, and so forth, and you have to follow up to make sure that the later installments of the projects are received. Many of the projects will have a midterm review or an annual review, and of course a final review sometimes. All projects will require a final report. Now, many of the agencies will send out this report for peer review and ask for a grade. And often this will determine the chances of success for future proposals. So again, it's a good idea to spend some time on this. And then, while your project is going on, start thinking about a follow-up proposal, especially if the work is going well. And then, you have to close the project, so you have to give the final accounts, publications, and they always ask you to acknowledge the funding of the publications that have been written based on work done on the project, patents, and how other results utilized can that be translated into some commercial activity or something similar. Is there a startup that is going to come out of the project work? So all these things would certainly be part of the closure of the project. So with that, of course, I hope I've given a very broad overview. I know many of you are already experienced in what I have said, but I hope that the few remarks I made will be useful for you. Thank you for your attention. And if you have any questions, I'll answer them over email. So good evening and enjoy the rest of the conference.
Okay, so yeah, I think like Professor Kakkar said, maybe if I think he's you can just search for his email ID. I'm sure you'll find his email ID, and we could probably write to him in case if there is a question directly for him. I didn't know that this 10-15% success rate. I thought it's much larger, but looks like over the years I think it has been decreasing. So not such a good news, because earlier I'm sure people could just write one proposal and they could get the money, but looks like things have become a little harder. So
I guess, Basa, this also depends on the type of grant. So probably for the startup research grants, it's slightly higher, but for core, it's on the lower side.
But but I know of cases where even the startup grants have also been rejected. So, therefore, I think writing a proposal doesn't guarantee the funding for sure. Whether it's at the core research grant, which is that's what Professor Kakkar was talking about, this 80 lakhs cap, or the startup grant. I think for both of them, there's no 100% success rate anymore, which I think was not the case maybe 10 years ago. So
I had a question about the CRG actually. So he did mention something about the cap, and he said 80 lakhs below and all. So what? So if you submit a proposal below 80 lakhs, it is just peer reviewed and you don't have to defend your proposal.
No, I think, see, we don't, no, I don't think that's what he said. He said that if it is more than 80 lakhs, see, the PAC committee that he was talking about, right? The program advisory committee, right? Or PAC, right? A chemical engineering pack or any pack. So the committee which consists of, which is part of this PAC, they can approve any budget up to 80 lakhs. Anything more than that, it has to go to a next level committee, which is a bit more. So what he was suggesting is, if you're looking for a funding, and you up to 80 is what you should really consider, because beyond that, it goes to next level committees. I mean, they don't know how really things work.
Had it been reduced to 50 or 60?
No, I mean, if it is 80, you are allowed to write 80.
80.
Yeah. I mean, this is like a sort of ballpark number. I also heard. Above that, I think they need extra kind of
approvals.
Whatever. Somebody, there is another layer of authorization needed. PAC can decide up to 80. Means you can write up to 80. Now they will decide how much they will give. It's not like if you ask 80, they will give you 80.
Yeah.
Does these grants also ask for
the last cycle that he was mentioning? I might be wrong again. I'll be happy to be corrected. The March cycle, the budget, the cutoff was mentioned as 50 or 60. No, it was not 80. So I was wondering.
For CRG.
Yes.
Oh, that is strange.
No, but I know people in the department who have got up to 73, 74 lakhs.
But when was it, Basa? Because March 2021, I was checking, and it was definitely not 80.
In
my colleague has submitted for, I think, asking for 90 lakhs.
Yeah.
19.
90.
Sorry. No, I don't know. They can ask. I mean, I don't think they have anything on asking. Like I can remember, I don't know whether now ECR is on or not. When the time I was asking for ECR, it has a limit of something like 59 or 55. I forgot.
See, I think earlier it was 55, but now I think they have made it up to 80. Is what I know of. Sunita, the particular thing that you are talking about, I mean, I also am not aware of, because usually when they ask for CRG, right? In fact, this up to 80 is again something that we hear from people. I don't think there's anything that says, look, you have to apply for. I mean, you can, of course.
So it is not written in the websites. So it's like what you just hear.
Yeah.
Okay.
So yeah.
And does these proposals go also for international review, or like it's mostly national?
What I know is that I think it's mostly been national, is what I know. Basically, I think some of the proposals are evaluated by the PAC itself, because the PAC consists of quite a few members, and all across different IITs, NITs, who have done very well in terms of getting funds and publishing and stuff like that. I think a lot of proposals are also reviewed by the PAC itself, and of course, they also, depending upon the project area, they either again seek one or two members of people who probably have applied for grants, for example. They pick up those guys and then ask for peer review. I know that last year, because of the COVID thing, some of the proposals they were just evaluated just based on the review comments itself. There was no, usually what you do is you submit a proposal, then you get reviews, and then they're going to call you for defending your proposal, right? Or make a proposal to the committee. Usually that happens, but it so happened last time because of the COVID, everything was based on the review comment that they had received. And I was told that, for some of the proposals, the reviews were as many as eight reviews per proposal. And then they took an average
and we
score.
do get to see the review report for, I think, this non-startup grants.
You mean the core research grant? Yeah.
Like the ECR or the other startup grant, we don't get to see the review report, that I know.
Okay.
I did not receive any review report for my ECR.
I also, yeah.
Okay. See, for me, the latest one I have not seen, but for my couple of earlier proposals, I have got a hard copy of the review reports every time I've gone for the proposal meeting. So therefore, I think maybe think, see, because I think because of this online portal, there could be some issue with, uploading stuff and things like that. But I'm sure that the reviews that they get play a very crucial role in whether something is funded or not. I think that's
yeah, and also it's like a good feedback, right? As Professor Khakkar mentioned. So it will be good to know the review reports.
Yeah.
And I have a question, like this final report, or let's say if you are asking for extension, who does evaluate these cases? This PSC, or they also send out to peers?
No, I think it's only the typically, see, what I know is this, okay, because see, we had somebody from the DST who kind of interfaces with one of the like say office which looks after funding for the external funding. So what they told us is that if you want any extension, okay, typically no cost extension are easily entertained. And if you want an extension, I think you should write 6 months before the formal closure of the project. Okay, that's what I know the rule is. Then you have to write to the see, because there's a particular scientist who handles all the proposals, right? Any communication that you have, it is actually not with the PAC, right? It is directly with the scientist who is affiliated to SCRB. So your communication on any of your project related stuff is with that person, okay? And therefore you would have to be in contact with him for anything. I mean, I think he's the one who's going to ask you for all these utilization certificates and stuff like that, right? I think I'm sure I think that your any extension related things have to be addressed to him. And if you want an extension, I think you should approach him 6 months before, is what I know. Yeah.
And this final rating on other, that must be PSC or peers, because that is, I think it's a collective.
Yeah, I think so. I think so. Yeah. So I think basically they look at some outcome. I mean, how many papers have been published? See, if you ask for like say 80 lakhs funding, and if you show maybe one paper, maybe probably one major paper, maybe they would accept it. But if you are looking at maybe a lower impact.
So there I had a question actually. So we propose certain objective in the proposal, be it experiment or otherwise also. It might happen many times that the directions change while we are exploring things and new results come up, and we start doing something like that. So when we submit the completion report, is there a tally made, like correlation, like what were our objective and what did we achieve at the end? And that's how and does it have an impact on the scores?
I think that's what Professor Khakkar's, I like Professor Khakkar's way of thinking about it, because he said the moment a project is sanctioned, you try and put as many as much manpower as possible, either in terms of BTech projects, MTech projects, PhD projects, and then also the hiring a project staff, right? I think as long as whatever output that you're going to show, if it is related to the project proposal, that in some way, right? It can't be that I've asked for I've got a project on self-assembly of nanoparticles, for example, and then I show some result on maybe I don't know, maybe polymer dynamics, for example. I think such things they probably it's easier to, but I'm sure as long as you kind of work around broadly that area, that should be okay. Because as he was rightly mentioning, see, sometimes you write up a proposal with certain objectives and a certain way the things evolve, and right, and it need not be that during the course of your initial experiments or simulations, you may find that maybe what you're doing may not work out. Maybe you may have to take some detour, for example. I think as long as you justify that, look, this is what was objectives, but for this reason, probably I have to change my objectives for whatever reason. I think the PAC is fairly. I mean, you see, it consists of probably your colleagues, right? I mean, you met with you know them in a sense, right? I think it's because it's a scientific community. I'm sure you should be able to explain things to them, and I don't think we should worry so much about it, as long as you've been able to make a good progress on some a project related to the proposal, and multiple angles and side deviation. I don't think they will mind so much.
I think what Professor Khakkar just mentioned briefly, that if you, want to keep things fairly broad in some aspects, so that we have a ground to cover sometime. He mentioned it as a point, that keep some of the points which is fairly broad, where you can squeeze your unexpected results in.
Sure,
Mhm.
sure.
Yeah.
So, Basa, I had a short question about this. So, I always have this this doubt over, because when I was writing my startup research grant, I was categorically told not to write on something that I have already done during my PhD or postdoc. So, nothing sort of an extension of what you have already done. And as compared to that, if I have to write about something that I have never done about, is like my like lack of experience in that field considered as a disadvantage. So if I have no, so for example, tomorrow if I have to work on biological materials, and I have never worked on biological materials, and my CV doesn't show any publications related to that field, is that a handicap when I'm proposing?
Yeah, that's a good question. I think that's a hard one to answer. But I mean, I don't think there's any rule like you cannot write up a proposal based on your PhD and postdoc experience. I mean, I don't think there's any rule like that. In fact, my first proposal, I had done work with the interfaces containing particles, and I looked at an extension of that. Only thing is, I said I'm going to look at external field effects and stuff like. See, you can't. I think given the training that you have had, I mean, if I had proposed something on working on say biological materials right away at that point, so people could also question, like you rightly said, right? People could question and say, hey, look, he doesn't have any background in that. I mean, how will he even show, right? So I think it's a good. I mean, I think there's no hard and fast rule as to you really should not work on any project that is not related to your PhD. I don't think there's anything like that.
Yeah, that is a problem because I mean, especially with regards to the startup grant, all you hear is hearsay. That uska grant reject hua kyunki usko bola gaya hai ki it is just a direct extension of your PhD. So then you get influenced by these things.
Yeah, that's what I also heard, but I think I heard like more a refined version of that. Don't do anything extension of your PhD. Of your postdoc, it's acceptable, and especially if your PhD is from India.
If your PhD is from India.
Exactly.
Okay.
If your PhD is from India.
That's the fine print. Huh?
These all are quote unquote something I would say.
No, because see, they don't want
popular belief.
two people within the country to compete with each other.
I mean, look